Thank you. Okay, hi everyone. So yeah, my name is Quentin Ficheux. Thanks for the introduction. And first of all, thanks to the organizer, because I think it's the kind of school which is really nice to attend, in particular at your career stage, I would say. So the topic of today's lecture is superconducting circuits, superconducting quantum circuits. So what are these things? So it's basically, first of all, do people had lecture on this already? Or? Okay, I see 1, 2, 3. Okay, so sorry, maybe it will be boring for you, but at least a good fraction of the room didn't have any lecture on that. So I can start from the basis. So these quantum circuits are electrical circuits which behave in the quantum regime, and they are made of superconductors. This is why we call them superconducting quantum circuits. So on this image, for instance, you see these small circles. And what they are actually antennas, so they are resonant antennas. So you see there's one main circle and there's like an outer part there, so there's a capacitance between them. And if you and we will see later on that if you look closely, there's a small inductive part here in the middle, and this is actually giving you both capacitance and inductance. So this is a resonator. So this thing resonates, and we'll see that it operates in the microwave domain, and we can operate it in the quantum limit. So therefore, this will act as a superconducting quantum circuit. So yeah, let me give you a brief introduction on that. So maybe I should start with some literature. So this lecture is heavily inspired from the paper here by Ciani Di Vincenzo Terral. You can find it on the archive. So there are also two good papers on the archive to read, which is the Quantum Engineering's Guide to Superconducting Circuits from MIT, and there is the Circuit QED review from Alexandre Blais from Sherbrooke. You can also find the lecture, so with the slides from Andreas Wallraff at ETH, and there are actually few books on the topic. So the first one is from Steve Gervin from Yale, and this is an intro to superconducting circuits. And this one is about quantum information, and the last one is about superconductivity. So we won't do a lot of superconductivity today, but we will mainly focus on the circuit part. So what's the goal of the lecture? The goal is to give you some idea on how you can use a quantum circuit, you can use electrical circuit in the quantum domain, and what's the formalism behind that. That's the main thing. And then to get you an idea of how it works, what's the technology behind that, and how you can use them to do something useful. So either an amplifier or a quantum computer or something else. And at the end, we'll try to see what happens if we try to build a quantum computer out of these circuits. And so there are some requirements. So I will expect that you have already seen what is a Lagrangian, an Hamiltonian, the basics of quantum mechanics, like canonical quantization, and also some basics on quantum circuits for algorithms. So yeah, so basically that's the storytelling that people come up with when you want to sell a quantum computer. You say that in 47 there was the first transistor, and this led to a Nobel Prize in 56. And this was a big macroscopic object. It was really slow, and this thing was actually a curiosity in the lab back then. But if you go from 56 to 71, Intel was selling its first processor with over 2,000 transistors. And it was way faster already. And the dimensions were much smaller. So this led to the first computer, so everything which is behind our phones, our laptop, and so on. And in 2011, you can find this kind of chips where you can actually don't see much. This is mostly an artistic view, and you see billions of transistors. They operate in the gigahertz frequency range, and their typical size is few tens of nanometers. So this is what's behind the so-called Moore's law, where you see the number of transistors on a chip. So this is a log scale as a function of number of years, and this is a line. So there's an exponential growth of the number of transistors on a chip, and this is like everything which is behind our computers, and this is what made this company so famous, and this is allowing us to actually show these slides with this PowerPoint on this laptop and this projector and everything else. And the question is, okay, what if this law fails, and if we cannot go beyond this? Is there something else we can do? What about quantum physics? So can you take this object and put them in the quantum domain? So So then there was some attempt to build some superconducting quantum chips, and so this is a few selected chips. So for instance, you see there are two main actors. So there are academic actors such as ETH Zurich. So I will explain you this chip in details later on. There are, for instance, TU Delft. There's also a big effort in Chalmers in Sweden. And so there are many academic labs. And on top of that, you have companies such as IBM, Google, IQM, and the University of Science and Technology in China. And the first thing you see is that if you're an academic, you actually show your chip with all the design. You list all the performances and you explain how you build it. And if you're a company, you show an artistic view or just the backside of a chip, and you don't really show the details. And you also claim that you're going to reverse climate change using your quantum computer. But this is, okay, I had to make this joke, but okay. But basically, we are doing the same thing, essentially. Not with the same manpower, not with the same technology exactly, but this is essentially the same. And the current status is that we are able to control about like 100 quantum systems at the same time in this system, and with some finite performances, and I will tell you more about the performances. And so I would like to insist on the fact that you should not necessarily go and do this thing, so build a quantum computer right away. There are a lot of interesting things you might want to do with these circuits. So for instance, you will see how to treat this kind of object. This is a transmission line with circuit elements, and this can be used to create quantum limited amplifiers. And they can be very useful for many applications, such as astrophysics, detecting, for instance, the cosmic microwave background. All this is detected using quantum limited amplifiers. You can actually couple them to some mechanical parts, such as membrane, or you can study the physics of a point contact like this one. And of course, you can also treat this microwave photons as light. So you can do all the quantum optics experiment and use this circuit to draw some beam splitters and do all the quantum optics as it was done with actual photons, like 10, 20 years before that. And I will talk at the end a little bit about quantum error correction and what you can do with quantum simulation with this circuit. Okay, so that's the outline. So I will start with the quantization of electrical circuits. I will tell you about quantum bits and oscillators. We'll see how to operate this circuit and the quantum operation. And finally, we'll try to build a quantum computer. Okay, so that's chapter 1. So the first question is everyone familiar with Lagrangian and all this? Yes? If you are, raise your hand. Okay. Not everyone. Okay, so I'll do a brief summary on this, and I expect that you know all this. Otherwise, it's going to be difficult. So if you start with mechanics, you start with a massive particle with mass m, and this particle is moving in a potential u of x. So you can think of this potential as a parabola or any arbitrary potential like this, and you have a mass somewhere which is given by m. So this particle has a position x and a velocity x dot. And now you want to write the kinetic energy of this particle. So the kinetic energy is given by T of x dot, which is nothing but 1/2 of m x dot squared. And the potential is u of x. So it means that the Lagrangian is nothing but, so it's a function of x and x dot, is nothing but T of x dot minus u of x. Okay, so how do I write the dynamics of this particle? No, how do I go from Lagrangian to dynamics? Yeah, so you can write the equation of motion, which is Euler-Lagrange. So it takes the following form. So that's the time derivative of the partial derivative of Lagrangian with respect to x dot minus the derivative of Lagrangian with respect to x equal to 0. So in our case, it just means that, okay, dr dt of mx dot. So if you take the derivative with x, that's the derivative of u with respect to x. There's a minus there, so if I put it on the right side, there's a minus. So it's minus du dx So that's the gradient of the potential, and the gradient of the potential is just the force. So that's a Newton's law. Okay, easy. Okay, now the question is, how do I go from this to quantum mechanics? Anyone? How do I go from a Lagrangian description to quantum mechanics? Yes, you need to quantize. So there's a procedure introduced by Heisenberg in 1927, which is called canonical quantization. And what do I need to do canonical quantization? Commutation relation, that will come later. Yes? Yes, you need to write the Hamiltonian. So there is a conjugate momentum, which is the derivative of Lagrangian with respect to x dot. This I will call P. So if I take this, I will just get mx dot. Okay. So then I can write the Hamiltonian, which is P x dot minus L, and this is just P squared over 2m plus U of x. Okay, so that's just the energy. And of course, I have some commutation relation. And the commutation relation is just that the Poisson bracket between x and p is equal to 1. Okay. And this now I can quantize. So I can quantize this, and what does that mean? That means that I can promote the operators. So I can promote x to an operator x hat, p to an operator p hat, h to an operator h hat. And also the Poisson bracket I can turn into a commutator. So basically I will get that x becomes x hat, p becomes p hat, h becomes h hat, and the commutator and the Poisson bracket becomes 1 over I h bar of the commutator. And what does that mean? That's very simple. It means that I have an Hamiltonian operator, which is just h hat is p squared over 2m plus u of x hat. And the time dynamics, which was given by the Poisson bracket, is now, so it was x dot is equal to the Poisson bracket of h and x. This is now I h bar dx dt is equal to commutator h and x. Okay? So that was the Hamilton equation, and this is now the Schrödinger equation in Heisenberg representation. Okay? And importantly, the other thing is that the Poisson bracket here, x and p, now becomes x hat, p hat is I h bar. So that's really important that you understand that, because we're going to do that with circuits. So what does that mean? That's fairly simple. I took just a particle, a one-deep mechanics problem. I can write the Lagrangian, deduce what's the conjugate momentum, write the Hamiltonian. Then I have a procedure that allows me to go from a classical Hamiltonian to a quantum Hamiltonian. I just basically put hats on the variables and the conjugate momentum. And then the classical mechanics given by the Hamilton equations becomes the Schrödinger equation. And importantly, the classical variables now they do not commute. So it means I have Heisenberg inequalities. I have some incompatibility between measuring position x and momentum p. And all that is a systematic procedure. So that was done for mechanics, but I can try to apply that to circuits. So this is the first thing we're going to do. Okay. So if you have any question, feel free to interrupt. So let's start. So let's do the same thing, but for an LC circuit. Okay, so I will tell you the basics about LC circuit and how we treat dipole nodes and branches. We're going to do this the same derivation for electrical circuits and quantize it. Then we'll see the Joyce-and junctions and how we can make an oscillator with the Joyce-and junctions. And later on, I will tell you a general method to treat electrical circuits in the quantum domain. Okay, so usually when we deal with circuits, we have capacitances, inductances, You can have an impedance, you can have voltage sources, current sources. Now there will be something more. So we will have a new element, which is a Josephson junctions there, which is symbolized by a cross. And since we are dealing with superconductors, we will try to not have any resistor anywhere. So if I treat the usual LC circuit, okay, so this is a single degree of, so this circuit with just a single degree of freedom. So I just have one node there, and this is the ground down there. So I have the inductor, and there's a voltage drop on the capacitance, and there's a current circulating this way. So I can write the usual dynamics. V is L di dt, and I is minus C dV dt. So V double dot is just nothing but minus omega squared V. And same for I. So I can define the resonant frequency, omega, the angular resonant frequency, as 1 over square root LC. And then, so I can write the energy, or the classical Hamiltonian, as CV squared over 2 plus Li squared over 2. So that you know very well, right? And if I introduce other variables, which are the charge, so Q is CV and the flux, phi is Li, I will get Q squared over 2C plus phi squared over 2L, which is just the same thing. But I will actually use these other variables Q and phi rather than V and I to go to the quantum domain. So in general, if you have a branch, okay, so imagine you have a branch, you can define two nodes, a start node there and a finish node there. So you need to give your branch some orientation. So you go from bottom to up. And then you define a voltage here, VB of t, and there's a current circulating in the opposite direction, IB of t. So you can define a generalized flux, okay, which is just the integral of the voltage. So we saw earlier that the voltage was d phi dt. Okay, so here's just the reverse relation. So that's just the integral of the voltage between minus infinity and t. So this is a new electrical variable, the phi b of the branch. And just like the voltage drop can be expressed as the difference between the voltage on the finish node minus the voltage on the start nodes, you can express the phi of the branch as the phi on the finish node minus the phi of the start node. Okay. And of course, you can write the Lagrangian of the circuit, which is not a function of x and x dot anymore, but a function of phi and phi dot. And this, you want to write it as a kinetic energy, T, minus a potential energy, U. The kinetic energy will depend on the derivative of phi, namely the voltages, and U will depend on the phi themselves. And you will have Euler Lagrange, which is giving you the equation of motion, and you can define the conjugate variable in the same way we did it, and you can apply Legendre transformation to get the Hamiltonian of the circuit. Do you have a question? Yeah, so how would you define T0? This is a convention. So here, the convention that I did not make explicit is just that all the voltage, the currents, and the flux, they all go to 0 when t goes to minus infinity. But you can also fix it to a t naught if you want. If you have any other questions, feel free to interrupt. Okay, so that's the general thing I can do. And here I also said that it's actually a set of phi b and QB variables, because I'm already thinking that my circuit might have multiple branches and not just one branch. Okay. So in general, if you have a branch, you can define a branch to be inductive if there is a relation between the current of the branch and the flux of the branch. So if there is a function g that relates current to flux, such as the case of linear inductor, so I of IB is phi b over L, then we call this an inductive branch. In that case, we can calculate the energy. So the energy is an integral of I and V between minus infinity and t. And then we just find that I is just by definition g of phi b of t prime, and V is just d phi dt. Right? So this is just the integral of g. So in the case of the inductor, this is the integral of phi b over L, which is just phi b squared over 2L. So we recover the usual potential energy of an inductor. A capacitive branch is a branch that relates the current to the derivative of a function of the voltage. And the voltage is a derivative of phi b. So for instance, we have IB is C dVB dt. And we can do the same calculation of the integral of I and v. And we just find that we have that we just recover the function f. So here we have c phi b dot squared over 2, which is just the kinetic energy associated to the capacitance. Okay. So if I do it for this LC circuit, a simple LC circuit, the kinetic energy, as we saw, is c phi dot squared over 2. And u is just phi dot over 2L. So the Lagrangian is just the difference of the two. And we can write the Euler-Lagrange equation. So we can take the derivative of phi with respect to phi dot and the time derivative of that. So this is c phi double dot. And we can take the derivative of this part with respect to phi, and we just find phi over L. So that's the equation of motion expressed in phi. And actually, that's just the current conservation, because phi over L is the current going through the inductor, and c phi double dot is just c v dot, because v is a phi dot. So this is just the current going through the capacitance. So this equation is nothing but just the current conservation, telling us that the current flowing through this branch is equal to the current flowing through the inductor. Yeah. And we can calculate the conjugate variable as the derivative of Lagrangian with respect to phi dot. And without any surprise, we find CV. So the conjugate variable is just the charge on the capacitance. Okay. So you will see that this is not always the case. So I will give you examples later on, which are actually showing us that this is not always just the electrical charge there. And if we calculate the Hamiltonian of this circuit, we just recover what we saw earlier with the usual relation that we have, q squared over 2c plus phi squared over 2l. Okay, so now what do we do? Yeah, we quantize it. So we do canonical quantization. So how does that work? So first of all, you have to make sure you found a set of independent variables. If the variables are not independent, this will fail. And then you have to apply that not to the Lagrangian, but to the Hamiltonian. So it means that you have to calculate correctly the conjugate momentum associated to each variable. And then you can directly replace the phi with phi hat, the q with q hat, the h with h hat. And the Poisson bracket, so here's the definition, can be replaced with a commutator. And this is great, because the Poisson bracket is giving you the commutation between the variables, but also the time dynamics, as we saw in this example. So in the case of our electrical circuit, we have this. So we have the phi I qi is now ih bar delta ij. And the time dynamics is now given by the Schrödinger equation in the Heisenberg picture. So this is really the same procedure than what we did for the mechanics problem. So in practice, it means that this is now a quantum Hamiltonian for this LC circuit. The phi and q electrical variables are not commuting anymore. So that means that now we have 0-point fluctuation of phi and q. Okay, so the charge is not perfectly defined. We cannot measure at the same time the flux and the charge infinitely precisely on the same circuit at the same time. So you have Heisenberg inequalities, and you can actually write this as also some commutation relation on the voltage and current of this object. Okay, so this is basically the equivalent of this mechanics problem applied to an electrical circuit. So now the question is there anything interesting we can do with this? Well, not so much. So why did I do that? Actually, I prepared for introducing a new element, which is the Josephson junction. So, okay, sorry. Before going to that, I just will introduce some new variables, which are dimensionless variables. So instead of using phi and q, I can normalize phi by phi naught, and phi naught is just h over 2e, a ratio of fundamental constant. So this is, so I did not say it explicitly, but phi is a flux, so the unit is a Weber, or volt times seconds, okay? And phi naught, which is just the ratio of h over 2e, is about 10 minus 15 volt seconds of Weber. So that's called a flux quantum. And so you can normalize phi to a small phi, which is now dimensionless, because it's a ratio of two quantities in Weber. And the charge, q, you can normalize it to 2e. And why 2e? Because we are dealing with Cooper pairs, so the charge of a Cooper pair is 2e. So that's how we normalize it. And if you write the same Hamiltonian that we saw earlier, with this dimensionless unit, we typically write it as 4 EC n squared plus EL phi squared over 2. And phi and n are now dimensionless, so the commutation between them is just I. And we usually speak about these energy scales as charging energy, inductive energy. And if we write it in this form, the 1 over square root LC of this oscillator is now written as square root 8 ECEL. So this is a little bit historical. There is a 4 which is there. There is a 8 in the frequency, and this is all for because of the choice of units for charges. But this is what you will find mostly in the literature. Okay, so now let's go to the Josephson junction. So what is a Josephson junction? Anyone who knows what is a Josephson junction? Yes. Yeah. Exactly. Yeah. Yeah. Exactly. So yeah. So in practice, a Josephson junction is just that you take a wire, a superconductor, so this superconductor usually we attach to it a phase, superconducting phase. Let's call it phi 1. You take another one, and this other conductor has a superconducting phase phi 2, and you bring them together close enough so that Cooper pairs can tunnel from one to the other, and that's a Josephson junction. And as it was mentioned, it has some nonlinear properties, and this is what will be useful for our circuits. So in practice, this is the electrical representation of a junction. It's a cross inside a square. So it means that usually we divide it into two parts, something which is purely a cross with just the inductive part, and a capacitance, because if you put two wires close to each other, there will be a capacitive coupling between them. So the main, one of the properties of this junction is called critical current, IC. The critical current is just the maximum current you can flow through this weak link. And if you send too much current, what happens is that the Josephson junction is no longer a superconductor and it turns normal. So it's just a normal resistor, a tunnel barrier. And so typically this critical current, you can pass 10 to 100 milliamp in this junction, and the capacitance of the associated to the junction is typically of the order of 50 femtofarad per micron squared. So you will see the dimensions of the junctions later on, but this is a relatively big capacitance per unit, per area, if you want. And if you measure it at room temperature, which you can do, you will find just a regular resistance with a resistance of a few kilo ohms. So in 62, Josephson predicted the two Josephson relations, and they are the following. So if you treat that as a branch, the current in the branch is just given by IC, the maximum current you can flow in the junction, multiplied by sine phi, curve phi. And what is this curve phi? The curve phi is phi 2 minus phi 1. And phi 2 minus phi 1 are the superconducting phases associated to the two superconductors. But we're not going to go into the theory of superconductivity today, as I told you. And this is very convenient because you have the second Josephson relation, and the second Josephson relation is relating this phi here, the derivative of this phi with respect to time, to an electrical variable, which is the voltage. And VB, we saw that this is actually phi generalized flux, the capital phi dot. So the phi dot is basically proportional to the curve phi. Okay. So let's just combine the two relations together. So yeah, we treat this junction as follows. So we say this is the first relation, this is the second one. We saw that the voltage here is actually capital phi dot. Okay, so it means that we can just replace this phi here by IB is equal to IC sine of the capital phi. So this is what we saw earlier. This is a function that relates the yes. B was the index I used earlier for the branch. So yeah, so this, for instance, all this B there is for a given branch. So what we saw here is that the current in the branch is just the critical current times sine of the phase generalized flux phi B in the branch. Okay, and we saw this is a relation between the current and the phase. So this is a current phase relation. So this is an inductive branch. Okay. So this thing, just by definition, is an inductive branch. And the function is nonlinear. So this is a nonlinear inductor, which means that the inductance of this thing depends on how much current you flow through the junction. And if you try to calculate this energy to be able to write the Lagrangian of this object, then what you find is that you find the integral of I times V, and this is just the integral of the sign, so it's minus EJ cos phi. And if you expand that, you will see later on that this is useful for a small phi. You just recover a constant term plus something which is phi b squared. So this looks like an inductive energy. So in practice, we'll talk about this Josephson energy, which is in front of the cosine there, EJ, and this has values between 2 and 200 gigahertz. And the typical inductance associated to this junction is 1 to 100 nanohenry. Okay, so just a word on fabrication, so I don't have enough time to talk about fabrication. So how do we fabricate these objects? Basically, we take one wire of aluminum there, and we're going to oxidize it. Okay, so you have a tunnel barrier here, so this is just aluminum oxide. And we deposit a second electrode of aluminum. That's the idea. So for instance, this is an actual scanning electron microscopy picture, so where we have a first layer of aluminum, we oxidize everything there, and we have a second layer, and here you have some overlap, and this is where the Josephson junction here. So typically we use superconductors which are aluminum, sometimes niobium tantalum, and the barrier is almost always aluminum oxide. The thickness of the barrier is typically nanometers, like 1-2 nanometers, and the way we fabricate them is usually by lithography. So it means we take a wafer of silicon, we put some plastic on it, which is just a resist. Then we go to a lithography machine, either laser lithography or electron lithography. We draw some pattern, and we try to, for instance, in this case, to suspend a bridge. So there's just two sides of plastic, and there's a bridge between them. And then we're going to deposit aluminum with an angle. So we have this first layer. There's the shadow of the bridge there, so there's no aluminum there, and there's aluminum again here. We oxidize everything on the surface, and we deposit a second layer with the opposite angle. And then what you get is that you have a first metal, you go through the barrier, and you go to the second metal there. So this is a Josephson junction. Yes?
What is the reason why you can't directly mask, just mask on top of the silicon and then deposit the aluminum and remove the mask and then deposit again? Is there a reason why you're using the shadow?
No, so there are many techniques. So there's the shadow technique is called Dolan bridges sometimes. There's Manhattan style. There are overlap junctions, which is probably what you mean. So overlap junction, you put a first layer of aluminum, you strip the resist, so you remove the plastic. The aluminum will oxidize to air, okay? And then you do a second layer of resist, and you make sure there's some overlap with what you're going to expose on the second step with the first one. But then you need to remove the native oxide. So you need an extra step to remove the native oxide, because this is really dirty oxide. You oxidize again in a controlled way, and you deposit a second layer. So this works. But you have 2 steps of fabrication. Okay, so this is how typically we fabricate that, and yeah, just to give you some idea on where this is done. This is an example of a clean room. So the images are yellow because we have UV filters. It's not just a bad camera. And so we dress up in blue. And this is just to avoid putting particles on the chips. So we are dealing with very small dimensions, like tens of nanometers. So this is why you need to avoid any dust. So we wear these fancy these funny dresses. And this is an example of chemical benches where we can deposit or strip the resist. This is a laser lithography system, so this is just a box in which you're going to place your sample and you will draw some pattern with your laser on it. And this is a deposition system where you can actually deposit aluminum under an angle or oxidize your aluminum. So, yeah. And so if I try to use this junction and put it in an oscillator, so imagine I replace the inductor of the LC circuit with a Josephson junction. And I will neglect the capacitance of these junctions. I can do the same exercise than before. I can write the Lagrangian. So I have the kinetic energy, C phi dot squared over 2. And now for the potential energy, instead of the minus phi squared over 2L, I will get this plus EJ cos phi. So I can, again, write the classic dynamics of this circuit, C phi dot squared. So you remember, C phi dot squared is equal to C dV/dt. Okay? So this is the current in the capacitance. It's going to be equal to IC, so minus IC sine phi. and IC sin phi is just the current in the branch of the adjacent junction. So this is just current conservation, if you want. Okay, this is just a side remark. This is if we get back to mechanics, you can map this exactly to a problem with a potential, which is a cosine, and this is actually a pendulum. So it's like the equivalent of a pendulum. So we can go to the Hamilton operator in the reduced units. So this is for EC n squared. And now the inductive energy is replaced by minus EJ cos phi. And we have the commutation relation between phi and n. So the generalized flux in reduced unit and the charge in the units of Cooper pairs are non-commuting observable with 0-point fluctuations. And again, if we expand this in the limit of small phi, the leading term in this inductive contribution is just EJ phi squared over 2. So if you neglect the rest, you're back to the LC oscillator. It's just that it's no longer EL, inductive energy, it's EJ. I'm good. So if you have questions, again, do not hesitate. Okay, so now we can do a small exercise. We can say, okay, if I take this oscillator and if I connect it to a voltage source, what happens? So now we have two nodes, so it's not it looks like not a single mode circuits anymore. So in practice, it's actually this phi g here will be constrained because the voltage here is imposed by the generator to be Vg of t. So it means that Vg of t is just phi g dot. So if I try to write the Lagrangian of the circuit, what do I get? So kinetic energy. So the kinetic energy, I will just get, okay, maybe I should do it on the board. Is it too fast or is it too slow? All good. Okay, so the kinetic energy is the one given by capacitances. So it's just given by capacitances. So the kinetic energy is going to be C phi dot squared over 2. Okay. And there's the other capacitance, the one for the CG here is going to be CG phi dot minus phi g dot squared over 2. Okay, that's kinetic energy. What about potential energy? So potential energy, there is no potential energy in the branch of the voltage source. There is no potential energy in the branch associated to CG. There is one for the adjacent junction. We just showed that this is a minus EJ of the cosine of 2 pi phi over phi naught, where phi naught is the flux quanta. Okay. So then I can write the Lagrangian, which is L is T minus U. Okay. And I have another condition, which is that I have a voltage source. Okay. So it means that phi g dot of t has to be Vg of t by definition. This is imposed by the voltage source. Okay. Now the question is, what is the conjugate momentum? Is it still the charge? No idea. What's the conjugate momentum? So if I write Q as derivative of Lagrangian with respect to x dot, so it's not x, it's phi dot. I get something a little bit complicated. Yeah, which is C plus CG phi dot. CG Vg. Okay. So you see, this is an example where the conjugate variable associated to the flux is no longer just the charge on the island. It's actually the charge with a renormalized capacitance due to CG minus a term which is just given by the voltage source. So the drive is actually in the conjugate variable. And then I can continue and write the Hamiltonian of this. So feel free to do it. I think now you understood how it works. So this is what I'll get. So this is so Vg is phi g dot. Okay. The Lagrangian we could write it together. It's like this. The conjugate variable is this. Okay. And now if I write the Hamilton operator, I just get Q with the VG term there, the voltage source, which is shifting the Q, and minus EJ cos phi, and there's an extra term which is constant, and we don't care about this last term. So what does that mean? It means that later on we'll use this circuit to build a qubit. Okay, and this voltage source here with a coupling capacitance CG is a very good model for two things: either noise, yes. Yes, the good question. So this term here is an operator, so it's a Q with a hat. Okay, so if you apply, if you try to find, for instance, the wave function, this is a matrix here, so it does matter in the dynamics. Here, the same thing applies. It's a phi with a cos. So the cos, you can Taylor expand, and this is an operator. This last term is actually times identity. Yes, it's exactly. It's a time-dependent offset, but it has no impact on the dynamics. Okay, so yeah. So this model there is good because the VG of T can model a control line on the qubit. So if we want to do gates, we'll do that in chapter 3. If we are doing gates on this qubit, we're going to use this model there. Or if we have some noise, so you can say that VG is just a white noise, a random noise, or 1 over F noise. This will model charge noise, actually. So we're also going to use that in chapter 2. Okay, so now I can give you, so now this starts to be a little bit more involved. But now we are trying to touch a little bit what's a general method to treat electrical circuits. So in general, in some electrical circuit will just have nodes. Okay, so these are the dots there. Okay, and how do you treat a circuit when you don't know where to start? You can just decide that one node will be arbitrarily the ground, and then you can define what is called a spanning tree. A spanning tree is just a way to connect all the dots together only once. And so this is, for example, an example of a spanning tree. So this is the line in orange there that connects all the dots and every dot, but only once. You could use, for instance, this branch or instead of that one, for instance. That's not unique. And all the other branches in the circuit, you color them in blue and you call them chords. And this is very good to do this small circuit analysis for two reasons. Because to quantize the circuit, we need to have independent variables. See? So the number of independent variables is actually equal to the number of branches in the spanning tree. So in that case, we have like 4 branches in the spanning tree, so there are 4 independent variables in this circuit. And why we don't have more? Because you have 1, 2, 3, 4 chords, so it means that there are 4 loops. Okay? And the loops, you can apply the Kirchhoff laws so that the sum of all the voltages is actually equal to 0. Okay? So we find the quantum version of that if you want. So up to some matrices A and B, which are just orientation, so plus 1, minus 1, zeros, you get that the sum of the I reaching a node or the sum of the voltages on the loop is equal to 0. Okay? And you can just find a set, pick a set of independent variables in this way. And actually, so we are not using voltages so far. We are using flux, general flux. And this is just the integral of that. So if you take the integral of the sum of the voltages equal to 0 in the correct loops, this is the same matrix with the fluxes. And actually, you find what is it's called induction. So it's Lenz's law that the sum of the fluxes on the loop is actually equal to external flux through the loop. So we'll see that this plays an important role. Actually, we're just gonna select a set of variables, and we're gonna apply these laws to just treat external magnetic flux in this way. Okay, so this is a little bit abstract, so we're just gonna sum it up. So you can use some transforms, so it's good to be a little bit careful on how you treat the voltage and current sources. Then you pick a spanning tree. So there are many possible spanning trees. A good way to do it is use all the capacitances. So use capacitive branches. This makes all the calculation easier. And then you count how many chords you have. This tells you how many loops you have, independent loops. And you can apply the Lenz's law to just take into account the external fluxes in these loops. And then you can write the Lagrangian, deduce the conjugate variables, and quantize the circuit. Okay. Yes?
Could you briefly mention again the difference between the red and the blue?
Yeah. So this is your electrical circuit. So here I did not draw them, but this is maybe an inductor, this is maybe a capacitor, a junction there, and so on. You have nodes, yeah, and so you want to know how many independent variables you have. So you pick a spanning tree. Okay, so you say I will connect them in this way. So I will use this orange thing. Yeah? I could just use this and do this, for instance, to connect them. It's not unique. And then you can say, okay, I will use the voltage branch. So the voltage on each of these orange branches, and this is, for instance, 4 independent variables. Okay. And what do I do with the rest of the circuits? So I have these blue ones. So they are already there. I'm just coloring. I'm just changing the color for the circuit. And I just say, okay, I have now 1, 2, 3, 4 more branches that which are not part of the spanning trees. So that means that I have 4 independent loops. So I have 4 relations to write, and they will include actually usually fluxes in these loops. And this is how you come up with a set of independent variables. Is that clear? Okay. Okay, so the example that we'll use also later on is the squid. Yes?
So you mentioned at first that you will not go into superconducting theory or the BCS theory. So where does this, what we are doing, the diagram that we are touching, where does it face, or where does it stop explaining the phenomena that we can? When do we have to go to BCS theory?
Okay, so when the superconductor is no longer a good superconductor. So there are many possible scenarios. One of them is that imagine you exceed the critical current of your junction. So if the current you flow you force it to be greater than IC, then your junction is effectively a resistor and not a superconductor anymore. So all this fails. Another case is that imagine that we are operating at frequencies which are not very far from the superconducting gap. Then maybe some of the excitation will create quasi-particles. Quasi-particles are not Cooper pairs, but free electrons, so they will recombine, and this fails also. And also, yeah, so these are 2 simple examples, if you want. Okay, so we'll use this later on, which is, so this is called the squid. A squid is like 2 junctions in parallel. So this circuit is still, there's just 1 node to the ground and just 1 node which is free. So this is just still a 1-mode circuit. So you can say that the generalized flux on the left is phi L, the generalized flux on the right is phi R. But you see they are not independent. Okay? So if I want to draw a spanning tree, yeah, what can I pick? Well, there are 2 choices. Either I take the one on the left, okay, or I take the one on the right. There are 2 possible spanning trees. So let's take, for instance, we can use, for instance, the one on the left, okay? And then we'll get that the sum of the fluxes is actually phi x. So I can just apply this and write the Kirchhoff law in terms of fluxes. So phi L minus phi R and is equal to phi x. Now, if I want to write the potential energy, I will have the potential energy of the junction on the left and the potential energy of the junction on the right, which is just Ej cos phi L and Ej cos phi R. Then I use the property that cos P plus cos Q is cos P minus Q over 2 times cos P plus Q over 2. And this gives me the differences of phi L minus phi R over 2, which is just phi x there, times the cosine of the sum that I call phi. Phi is phi L plus phi R over 2. So this is effectively showing that this element behaves, gives me a potential energy, which is just a cos of phi, and a prefactor, which is minus Ej cos of the external magnetic flux. So this is how we use this circuit. So this is effectively a loop in which you can tune the Josephson energy, and the effective Josephson energy is just the 2 times the one of the junction times the absolute value of the cosine of external flux. And this is how we're going to tune the frequencies of our qubits later on. Okay. So yeah, to summarize this first chapter, so we saw how to apply Lagrangian, Hamiltonian, and all this, not just to mechanics, but to electrical circuits. So we didn't treat, for instance, mutual inductances, current sources, and there are many more things we can do. We saw the electrical variables phi and q instead of current and voltage, and we can actually translate them to dimensionless variables, which are small phi and small q, or n. Actually, I call that n. And we can do canonical quantization with these variables and put some hats on these operators. And we saw the Josephson junction, we saw the Cooper pair box Hamiltonian, or the Josephson oscillator, and we saw a general method to write the circuits. Okay, so some exercises that you can do at home. And so you can do the same thing, so the squid, but with two asymmetric junctions, EJ1, EJ2. So you write the same thing, and you're going to see this formula coming up. Okay? So you can do that if you want at the break. And okay, now in principle, you can do more complex circuits. So I gave you a general method. So in principle, you can use this and say this is a spanning tree in orange, and I can write the kinetic energy, potential energy of this thing. This starts to be quite involved, and I can write it as there are actually three branches, so there are 3 variables. I can write in the 3 variables, and this is actually a circuit which is used to build protected qubits. Okay, this one as well. So okay, this starts to be more involved, but this you can in principle do. Okay, so for instance, you have some metaphysical questions that you may ask, and we partly answered this already. If I take a LC circuit and I couple it to a Josephson oscillator, does it matter if I have a capacitance there? So at first, it looks like you have an extra node there, so maybe an extra degree of freedom, but with no inductive part associated to it. So you can answer the question relatively easily, are the 2 circuits equivalent? And probably the answer is yes, but you can show it. Also, you can treat semi-infinite or like infinitely long transmission lines like these ones, where instead of the telegraph model LC, you replace the L with Josephson junctions. And this is actually, so you have all the tools to do that, and this is the basis of traveling wave parametric amplifiers, which are used, for instance, for astrophysics applications. Okay, if you have questions, otherwise we go to chapter 2. Yes?
I'm still a bit confused about the spanning tree.
Yeah?
So it's not like you draw a loop throughout the circuit, right?
No.
So how exactly do you determine where the tree goes?
Yeah. For instance, here you see the nodes, so you put dots where you have the nodes. Okay, so you have a node here, which is the ground, a node there, 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 there. Okay. Now you need to imagine everything is black. You need to color a part of the circuit in orange so as to connect all the nodes and to connect them only once. So here is shown an example. That works. Okay.
Okay, but to go from, for example, phi A to phi C, then you also are connecting nodes, but those we don't draw.
So, yeah, so if I continue the spanning tree up to there, this node is connected twice, through the one there and through the one there. So I can do that. I can color this in orange, but I have to remove and put it that in black.
Yeah, okay, yeah, now I understand.
Okay. Okay, cool. So chapter 2. So the break is at what time? Okay. All right. Okay, let's go. Okay, so we saw LC circuit, we saw the LC oscillator, we saw the Josephson oscillator. So we're going to see a little bit more in detail what it looks like in an experiment. We're going to do second quantization to them, so to find exactly what we call a photon, what are the quanta of excitation in these circuits. We're going to see how we can measure them also. So what if you put that in an experiment? What are the requirements? Then I will show you the transmon qubit, which is the most widespread qubit in this system. And then we're going to look at what happens if you couple a LC circuit to a transmon qubit. Good? Okay, so we are back to the same LC circuit. So just to give you some numbers, so if you just take a wire in vacuum, typically it has an inductance of about like 1 nanohenry per millimeter. So we want the circuits to be small. So we're just going to stick to this value of 1 nanohenry. So if you take a capacitor, like parallel plate capacitor, with a size of 10 by 10 microns and a thickness of about 10 nanometers, so it's a quite compact capacitance. Yes? Okay, okay. So it's 10:30. Okay, cool. So we have more time for questions. So and so if you take a capacitance which is 10 by 10 micron with a gap of about 10 nanometer, and you take the dielectric to be aluminum oxide, then that gives you, with the parallel plate capacitor formula, a capacitance of about 1 picofarad. So it's actually quite comparable to the capacitances we have usually in electronics. So it means that if you calculate the frequency of the circuit, so you do L, so 10 minus 9, times C 10 minus 12, and you take the square root of that, and 1 over 2 pi, you just find a frequency which is about 5 gigahertz. So that tells you that this circuit, by basic dimension consideration, will resonate in the frequency domain of microwaves. Okay, so you have to use same frequencies than the 4G and so on. So you have to use microwave equipment for sure. And if you convert this energy to kBT over h, so sorry, this frequency to kBT over h, you find the temperature which is a quarter of a Kelvin. So that tells you that if you operate that at a temperature which is of the order of 0.25 Kelvin or higher, like room temperature, this will not be quantum, because these oscillators, they will be full of thermal photons. Okay. So it means that we need to operate them at temperatures which are well below 250 millikelvin. And we can calculate the impedance Z, which is just about like 50 ohm, of the order of 50 ohm. Okay, so we saw the Hamilton operator, Q squared over 2C plus phi squared over 2L. We have the commutation relation between phi and Q, which is IH bar. And so what we can do now is that we can try to see, okay, you have seen this problem with mechanics, like a spring. So P squared over 2M plus 1 half of Kx squared. Okay? So and you saw that you can define photons in second quantization. So here we can do the same thing. So we can say Q, the charge operator, we can write it with some prefactor, A dagger minus A. And phi, we can write it A plus A dagger with some prefactor. And so what are these A and A dagger? They will be the ladder operator, so so annihilation and creation of photons in our oscillator. Okay? And if we do that, so you find that the Hamiltonian can be transformed from two quadratic terms, so this Q squared and phi squared, into H bar omega A dagger A plus 1 half. So I assume you have all seen this formula, right? And of course, you have the standard relation, which A dagger n is square root n plus 1, and same for n. And A dagger A is just the number of photons. So now the question is like, what is this photon? So we are talking about, we are discussing about electrical circuits. So you will see in practice that this is what I like to call an electronic photons. So it's, if you want, it's a quanta of energy in the circuit, but it's actually, of course, an electrical excitation, but it's quantized. So if it's quantized, you are tempted to call it a photon, but this is still an electronic circuit. So let's call it electronic photons for now. And so then there is something else, like if you want to probe the circuit, so LC, so maybe you have photons there. How do you do that? So if you take a transmission line, so this is a transmission line, you can send a wave here, A in, and you couple this to a capacitance there. The wave will be reflected, and you have an outgoing wave A out. So I gave you the quantum equation associated to that, which is that this operator A and A dagger, if you look at them in Heisenberg representation, so the representation in which the operators, the operators are evolving themselves and not the states, you have the Schrödinger equation plus two extra terms which are related to the loss through this line and the input there of the incoming wave. And you have a continuity relation, which is that A in plus A out is square root kappa A. Yeah. So you can do that. You can treat the field classically, and you find something which is not surprising, which is just the usual response of LC oscillator. So this is something which you know, actually. You know that because, okay, maybe I should have shown this on the slides as well. You know that because if you have a classical circuit, if you have a transmission line, okay, you send a wave alpha in, it gets reflected into a wave alpha out, and then you put an impedance Z load. And you can say transmission line has a characteristic impedance Z naught. So what's the reflection coefficient there? What's the reflection coefficient? You know that, no? This is classical physics, yeah, so don't be afraid. This thing is just a Z load that can be, let's say, a function of omega minus Z naught divided by Z load of omega plus Z naught. This is the standard expression of reflection coefficient. So it tells you that if the Z load is equal to Z naught, there is no reflection, it's an impedance match. Otherwise, if it's greater or lower, you get the phase reflected, which is different, okay? So in our case, the Z load is just the Z load of a LC resonator. So that we know how to write easily, okay? And we can just write it with inductance and capacitances, and this gives us the very same formula in classical physics. So there is nothing quantum there, okay? And so what does that mean? That means that if the Z load has an impedance with a resonant frequency, it means that we have a phase jump. So if we hook up a network analyzer there, we send the wave in, it gets reflecting into a wave out. If you look at the phase of the reflected signal to the input one, so that's the argument of S of omega, you will see a phase jump at the resonant frequency of the LC circuit. So what is it in practice, this LC resonator? This is an example. So this is what we call a lumped resonator. Lumped means that it's a circuit in which you can clearly identify who's the capacitance and who's the inductor. So in this circuit there, you see like two big pieces of metal facing each other. So that's just a planar capacitance. And then you have a small wire with a meander, and that's the inductance. So this is L, this is C. Okay. And down there, you have a transmission line which is passing nearby, and this scale bar is 100 micrometer. So you can just send some microwaves there and get them reflected on this circuit. This is another example with a transmission line there, and you have just the same thing, a transmission line with two open ends, which is with a finite length there, and this is resonating at a given frequency. So typically what we find is that these circuits, they have a quality factor which is about 1 million. This is due to material properties, usually, material losses. The frequency, as we discussed, like 4 or 5 gigahertz. So it means that the lifetime of energy on the circuit is about 40 microseconds. So if I put one photon in the circuit, it will live for about a few tens of microseconds, typically. Okay. So we saw that the frequency expressed in temperature of this circuit is, yes? Yeah.
So it's like single photon readouts also?
So yeah, so I said if you put one photon there, it will live for about like 40 microseconds. So I did not say anything about the detection. Okay. So imagine that you can inject one photon, which you can do, or you can usually you apply coherent fields, usually not single photons. But if you displace the oscillator with a coherent field, or if you put one photon, it will live for a time of about 40 microseconds.
And this is different from the counter photon to the excitation. Like, can we think of this as the excitation lifetime, or is it?
Yeah, exactly. This is maybe that was not clear. This is the lifetime of the electronic photons, if you want. So if you want, this is a transmission line, so I can send an electromagnetic wave. Okay, it will enter this resonator. In this resonator, if I'm able to count photons, the number of photons is quantized. Okay, this is how you define a photon. And this photon will stay there for a given amount of time. For two reasons, either because it will escape and go back to the transmission line, or because it will die inside the resonator because this thing has some residual losses. Okay, and overall, this gives a quality factor of about 1 million, which means a lifetime of like 50 microseconds or so. Is that clear? Okay, so in practice, this is how we do the experiment. So we need to use a dilution refrigerator. So this is an example of one of them that we have in the lab. So this is a big machine. Actually, it's not so big. So it's about this size. So it's a tabletop machine. Okay, but there's a bunch of pumps. So if you have seen that in the lab, it's actually a big mess usually, and there's a lot of noise. And so there are different stages. Okay, and typically what is easy to achieve is to reach 4 Kelvin. 4 Kelvin, we just reach it with, by evaporating helium-4 on these plates if you want. So you can just bring in either liquid helium, or you can just flow some very cold helium gas. Or you can use a cold head, like in blue force fridges, where you make a very cold point by circulating helium-4, and you connect, you thermally anchor that to this plate. Okay? And then you need to use another mechanism. And the other mechanism is, if you want, the dilution of helium-3 in helium-4. So it's a little bit like, imagine you have alcohol in water. If you lower the pressure, the first thing that will evaporate is the alcohol, and you will be left with more water in fraction. And by doing that, you evaporate alcohol out of water, and due to interaction, you extract heat. The same thing happens between helium-3 and helium-4. And this is happening in this small box there, and this brings us down to about 20 millikelvin, which is significantly smaller than a quarter of a Kelvin, so we can actually operate our resonator in the quantum regime. And all the rest, all these cables there are just to bring the signals, to thermalize them with attenuators. And here we have a magnetic shield, here in gray, and inside that we actually have a sample holder with a chip on which you can pattern these resonators. Okay. So we saw that this is we can do this. We can have these photons in this LC circuit. Actually, we saw the Cooper pair box Hamiltonian or Josephson oscillator Hamiltonian, and in that case, what we'll see is that the potential is no longer a parabola, like phi squared over 2L, but it's a cosine. So we'll see a deviation from the harmonic potential, and this will introduce some nonlinearity in the energy levels, and this is what we will use to define the two-level system. Let me get back to this problem that we solved earlier. So we saw that if we connect a voltage source there with a coupling capacitance to this Josephson oscillator, we get this Hamiltonian. So the charge there in the kinetic part is displayed by CGVG. Okay, so that will make the momentum fluctuate if this is noise. Okay. So we can write it in dimensionless variables with the ng, which is CGVG over 2e. And we end up with an Hamiltonian, which is the following. So 4 EC n plus ng squared minus EJ cos phi. And if you want, this is, for mathematicians, this is a non-problem. So we can actually draw the eigenfunctions. So this is a matrix. Huh? So we can draw the eigenvectors and eigenenergy of this matrix. Okay, and look at what are the properties of that. So what we get is the following. So if we take the energy of this Josephson oscillator, we find that the first level here is in blue, so we call it the ground state. Yeah? And we plot that as a function of ng. So ng is potentially like the voltage is proportional to the voltage applied there. We see that this changes a little bit as we vary ng. If we look at the energy of the first excited state that we call E there, it's actually changing quite a lot. And same for F, and then it varies more and more. And this is done for a ratio of energy, which is EJ over EC of about 2. So this regime there was studied quite extensively more than 20 years ago. It's called a Cooper pair box. Okay? And this gives you a circuit whose transition frequencies or energies are actually quite dependent. So this is gigahertz. So the frequency is varying by multiple gigahertz as a function of the charge offset, ng. So we are in the scenario where this voltage source is actually a noise. Okay? So you don't control what voltage is applied. The voltage is applied by the fact that you have charges on your sample, and they are moving around. And this will display the charge on this oscillator there. And if this happens, the frequency of your qubit will change by gigahertz. So it's impossible to use that as a qubit. However, if you reduce, if you increase the ratio EJ over EC, you go from 2 to about 20, what you see is that these lines, they become straight. So G is almost insensitive to charge offset. Same for E, same for F, and so on. So actually, so the quantity we introduce is called charge dispersion, which is epsilon, which is the energy, the frequency of the transition G to E when the charge offset is 1 minus the transition frequency from G to E when the charge offset is 2. And this scales exponentially in the ratio EJ over EC. So this you can this you can show. Actually, it's quite involved, but you can look at this paper. So what does that mean? It means that if you want to have well-defined energy levels, if you want to have a qubit, you would rather use this regime. But why is it the case? It's the case because if you have a large EJ over EC ratio, actually it means that the junction is big. Okay, so the junction is not very inductive. So it means that mostly the phase fluctuation will be small, and this big junction is quite linear actually. So we are getting closer and closer to a LC circuit, and we know that in the case of the LC circuit, what we have is just Q squared over 2C and phi squared over 2L. So it's the same thing than if we calculate the energy of a particle in a displaced frame. Just offset by a given momentum offset. So this is not affecting the energy. So it's normal that if you want that as we approach the limit of harmonic oscillator, we become insensitive to charge offset. Another way of saying it is that these oscillations they are coming from the only thing that oscillates as a function of charge offset in the Hamiltonian. So this is the cosine of the junction. So this is exactly what we see. This is directly the cosine of the junction. So we're going to make this oscillator more and more closer to a LC circuit, and this is how we're going to operate that as a qubit. So let's do that. So this is still our potential there, and we want to treat this Hamiltonian, so the 4ECN squared minus EJ cos phi, and to write it in the operator, the creation and annihilation operator B and B dagger. Yeah.
And that introduces a non-linearity.
Yeah.
So if AJ is very large, shouldn't that mean that we expect more non-linearity?
Aha, good question. Okay, I will not go back to the previous chapter, but this is actually written in the previous chapter. So EJ is a prefactor in front of the cosine, okay? But then you will expand this. Imagine you expand the cosine in phi squared and phi to the 4. Okay. So if you want to know what's the nonlinearity, you want to look at the ratio of the term phi to the 4 to the term phi squared. And this, actually, if you use dimensionless variables, it's only meaningful to look at the ratio in dimensionless variables. You will see that it scales, it goes down as EJ goes down. So if you want, this EJ term here is just the amount of inductance you have. But I mean, so the bigger the EJ, okay, the bigger the EJ, the smaller the inductance you have. That makes sense. It's just like the inductive energy. So EL is proportional to 1 over L. Okay. So if you have a big EL, it doesn't mean you have a big inductance. You have actually a very small inductance. And for the same applies to the nonlinear effect. But if you want to quantify them well, so we will do that, you need to look at the ratio of the term order 4 to term order the second order. Yeah.
This, let's say, separation of energy levels and they were degenerate at some point and then not. This reminds us that somehow we have an effective potential. So that's what, let's say, differentiates a transform from a Cooper box, a Cooper pair box. In a sense, it has some potential energy.
Well, the two of them have potential energy, so this is the thing we have written multiple times. It's always minus EJ cos phi.
But here it's much stronger.
Yeah, so if you want, in the sense, the nonlinearity is much stronger there. So you can see that because, the frequency difference here between G and E and E to F is quite similar. Yeah, there, the two frequencies are very similar. But from there to there, you see this is very different. And if you change the NG, the difference is even higher. So if you want, this is this circuit on the right is way more linear than the circuit on the left. Another way of saying it is that if I want to drive my circuit, and I apply a short pulse, it's very easy that I will go from G to E, but also E to F, because the frequency of G to E and E to F is close by. But here, that will mostly never happen, unless if my pulse is extremely short compared to the anharmonicity. So this has a much higher anharmonicity. So is that your question?
Yeah, but in a sense, the separation between these energy levels is due to an increased potential, right? A higher value of interaction, or not?
So it's like, so there's just one system. There's just one degree of freedom. So you cannot really speak about interaction between multiple degrees of freedom in this circuit. So not sure. So we can discuss that in more details if you want. But you can have a look at this problem as a solid state problem with band physics. Okay, and then you can talk about like terms in terms of phi unit instead of position. And then yes, we can talk about interaction between the different wells. But this is just a 1D problem, so here at the level of just electrical circuit, there's no interaction per se. Okay. So let's go. So we start with the Hamiltonian we derived earlier, which is 4ECN squared minus EJ cos phi. And now we want to say, okay, phi will be B plus B dagger, and I will put some prefactor there, which is 2EC over EJ to the power 1/4. And the charge operator, dimensionless charge operator, N, will be B dagger minus B with a prefactor, which is EJ over 2EC to the power 1/4. Okay. And then I will inject these two things into that. Okay. This is quite difficult, mainly because of the cosine. So I will do something else, which is that I will expand the cosine. Okay. So in the limit EJ much greater than EC, you will see that the prefactor in terms of phi it becomes really small, so it looks legitimate to expand the cosine. And I will just keep the term phi squared and phi to the 4. Also, I will not put any NG there in the kinetic energy because we saw that in the large EJ over EC limit, the energies are not dependent on NG anymore. And if I do that, what do I get? I get just the harmonic oscillator, so 4EC n squared plus EJ phi squared over 2. So that we saw that this is h bar omega A dagger A. Okay? So this is h bar omega B dagger B, B dagger B. And the omega, we saw that this is just 1 over square root LC, but in the dimensionless unit, this is square root 8 EJ EC. Okay? So this is just 1 over square root LC if you want, but with the L of the junction and the C of the capacitance. And then the next term is minus EJ phi to the 4 factorial. So phi to the 4 will be B plus B dagger to the 4. And the power 4 there will cancel out this with this power 1/4. So we'll get 2 EC over EJ. And 2 divided by 4 factorial, so 1 over 12. So we just end up with this Hamiltonian there, which is just square root 8 EJ EC B dagger B minus EC over 12 B plus B dagger to the 4. Okay. So if you want, it's just an oscillator, usual oscillator, with a nonlinear term. Okay. And then there's a small calculation that I leave to you, which is actually not difficult but quite involved, is that if you apply the RWA, so RWA means you only keep the terms with the same number of B daggers and B's, you can show that you expand that and you do the RWA, you just have these two terms. So you have one term which is 12 B dagger B, so this will be combined with this one. And there's a last term which is B dagger B, B. So if you combine everything together, you get the frequency there of the oscillator minus EC over 2 B dagger B, B. So it's called a Duffing oscillator in this form. So this exists in classical physics as well. Okay, and now we can try to see what can we say from this Hamiltonian directly. So if we calculate the frequency of, so the energy of the zero state, this term doesn't count because you have two B's there. So B applied to 0 is just 0. Same for 1 because B applied to 1 is 0 and B applied to 0 is 0. So this is from 0 to 1, this is just the frequency of the harmonic oscillator. So we just derive an expression, analytical expression for the frequency of the qubit as a function of EJ and EC. So typically that will be 4 to 8 gigahertz. And the anharmonicity, so the frequency of the 1-2 transition to the 0-1, will be just given by this term there, which is the standard result for a Duffing oscillator. And typically, it will be a fraction of the frequency, so typically 0.2 gigahertz. Okay. So what does that mean? That means that we have this thing, which is a Duffing oscillator, and this is just an expansion of the Cooper pair box Hamiltonian in the limit of EJ much greater than EC. And this means that in practice, you have F01, and F12 is slightly different than F01. So it means that you can use these first two levels to operate that as a qubit. Okay? So to identify the qubit Hamiltonian, we map the bosonic operators there of the Duffing oscillator to Pauli operators. So I expect you are all familiar with Pauli operators, right? So for instance, so B dagger B, we saw this is the number of photons in the oscillator. So the equivalent of the photon number for a qubit is just the sigma z operator. So actually sigma z goes from -1 to +1, so the number of photons in the qubit is sigma z over 2. So B dagger B we're going to replace with sigma z over 2. And so the equivalent of the position is B plus B dagger, if you want. So that we'll call sigma x for the qubit. And B dagger minus B, we're going to call it I sigma y. And if we have this description with just the first two levels and the spin and the spin 1/2 operators, we're just going to remove the B daggers and B and higher order terms. And in the qubit approximation, we just find that the Hamiltonian is the frequency we derived times sigma z over 2. And we remove all higher terms. Okay, so just a quick reminder on the block sphere. So you saw that maybe in the previous lectures yesterday. So who never heard about the block sphere? Okay, cool. So there are two conventions. Either the ground state, you put it to the south pole or you put it to the north pole. Okay, so in my case, I will put it to the south pole. Okay, feel free to disagree, but in this slide, the ground state is there. So it means that if I'm down there, I'm in ground state. Okay, easy. So we have the Pauli matrices. So there's the identity. There's sigma x 0, 1, 1, 0. There's sigma y 0 minus I 0, and sigma z 1, 0, 0, 1, 0 minus 1. And the density matrix of the qubit, we can write it in block coordinate as follows. So it's a 1/2 of identity x sigma x plus y sigma y plus z sigma z. So if z is equal to -1, I'm in the south pole. So it means that I have identity minus sigma z there, and divided by 1/2. So I have just 0, 0, 0, 1. Okay, so the basis is 1, 0 in this representation. Okay, now if I do a superposition, so plus state, which is 0 plus 1 over square root of 2, I will just get x equal to 1, okay, and all the other terms are equal to 0. So I'm just on the equator. I can be in the, I didn't put, but we can have the plus I states, which is 0 plus I 1 over square root of 2. We can have the 1 state, which is north. So, and this is just the same thing with a plus there. Okay. So now we derive, if you want, without skipping too much steps, how we go from an electrical circuit to a qubit. And we can look at actual implementations. So there was this Cooper pair box already. This is back from 1998, where we had 2 Josephson junctions here and there, and a capacitor. So this is not what we want to use. This is in the small EJ over EC limit. So, and then you have basically many different flavors of qubits. Some of them are called 2D because they lie on the planar chip. Some of them are 3D because there's an antenna, and this lives into a 3D box in aluminum in that case. And basically, they all have fancy names, but they are all the same electrical circuits. And usually, the names comes from the shape of the capacitance. So you have X-mons, which are just transmons, but with a capacitance that looks like X. Or some people call this one Jellymon. Okay, whatever. But, okay. So you have many flavors of qubits, but they all have the same Hamiltonian in that case. And you can just design the parameters with some fancy softwares and get fabricated. Just to mention it, there are a lot more different qubits than what I described. Okay. So there are flux qubits. There is the fluxonium. The fluxonium is yet different electrical circuits. Okay, this is, for example, a current mirror qubit, which is a very long qubits with some fancy topology. There's the 0 pi qubit, which was in one of the exercises earlier, which is just this triangle with a bunch of capacitance, inductance, and junctions. There's what people call the unimon. There's the cat qubit, and okay, I will not have time to discuss it in details, but there are many more types of qubits. In the end, in one description or another, you always end up with poly operators and a block sphere sooner or later. But usually the initial derivation and the way it works and the sensitivity to noise is very different for each qubit type. Okay, now we're going to get to circuit QED. So the question is, what happens if you couple this kind of Josephson oscillator to a LC circuit with a capacitance? And I will assume that the coupling capacitance is much smaller than the capacitance of the circuit and the capacitance of the Josephson oscillator. So here we go. So it's a little bit of math. Okay, we did quite a lot. The second part of the lecture will be not so much math for sure, and more pictures. And so we're going to get kinetic energy as usual, some potential energy from the junction and the inductance there. We calculate conjugate variables as always. We write the classical Hamiltonian, and we turn that into an Hamilton operator. Okay, what do we see? We see that we have the LC circuit there, we have the Josephson oscillator there, and we have the coupling between the two, okay, which is just 8 ECC, so coupling capacitance, charge operator of R, charge operator of Q. What does that tell you? That tells you that all this we already derived and we already did it, and there's nothing new. And there's just this coupling term there. It tells you that when you have a capacitance, a mutual capacitance there, well, there's nothing fancy. You just couple the two charge operators, the two charges on each side of the capacitance. This is quite natural. And then you can redo the same derivation that we did. So this part there for the LC oscillator, you can turn into h bar omega et Lagrave. This is done there. This part there for the transmon, you go through the B's and the Duffing oscillator, you turn that into poly operators, you end up with a qubit. And now the only thing which is left is the interaction. And the interaction, we saw that the charge operator of the qubit is like a position, and the position becomes a sigma x. Charge operator of the resonator becomes A plus A dagger. So this is all showing you that this circuit is actually something called the Rabi model, where we just have an harmonic oscillator, a qubit, and we just couple them with an Hamiltonian term, which is sigma x A plus A dagger. And then what we can do is that we can usually we can do a small approximation. So we can use the ladder operator, sigma plus, sigma minus of the qubit. So I remind you, sigma plus is sigma x plus I sigma y divided by 2. Sigma minus is sigma x minus I sigma y divided by 2. So sigma x is just sigma plus sigma minus divided by 2. Not divided by 2, sigma x plus sigma minus. So you put it there. You just apply RWAs, so you get rid of the terms which are destruction, destruction, creation, creation, and you just have the swap operator, so creation, destruction, destruction, creation. And this is called the James-Cummings model. Okay. So all that to say that this circuit, yeah, in principle you know how to treat now rigorously, and this gives you an oscillator, a qubit, and a swap interaction, which is called James-Cummings. And this is beautiful. This is beautiful because back in the days, this is what gave the name of the field. So the field is called circuit QED, in analogy with cavity QED. And the reason for that is that what people did, for instance, you can look at the book, very good book, Exploring the Quantum by Serge Laroche and Jean-Michel Raymond. So they got a Nobel Prize for that, is to look at what happens when you take a microwave cavity and you put actual atoms in there. And they managed to use the Rydberg atoms with a very large dipole moment, and this allowed them to achieve a strong coupling of light and matter. Okay? And this was a quite spectacular and very good achievement back then. So they have this cavity, they have a coupling rate G between the atom, between the light and the atom. The cavity loses photons at a rate kappa. By the way, their cavity is much better in terms of quality factors than ours. and the photons can spontaneously emit some radiation gamma. Okay. And what's surprising in that they do the same treatment, so they derive the Hamiltonian, and what they find is just Jens-Cumming Hamiltonian, the same than the thing we just derived. And so in our case, this is the following thing. So the cavity is just the LC circuit there. So this is where we have photons, the electronic photons that we discussed earlier. It can leak photons to the outside. This is just a transmission line. So this is the wires you saw in the fridge. And so there's a coupling dipolar moment there with the electrical field. This is just the coupling capacitance there. And the atom is replaced by a Cooper pair box, or if you want, a Josephson oscillator that we treat as a qubit. And it can have some internal losses, which can be a resistor there. So we get the exact same physics. And there are some differences. One of them is that for us, it's very easy to go to strong coupling. And the reason is that the coupling G is just given by capacitance. So you make the capacitance bigger, and you are in strong coupling. And so back then, they saw like two main limits, okay? So they defined the detuning at the frequency between the resonator and the qubit. And when the two have the same frequency, we say the detuning is 0. Then we have dressed states and vacuum Rabi oscillations. So it means that if there is a photon in the qubit, it will oscillate and go in the cavity, turns into a photon, and then comes back in the qubit. Okay. So here the same thing happens. If the circuit there and there have the same frequency, you will have an excitation there that will oscillate and come back there. Then there's the dispersive limit that we will use later on for quantum computation application and readout in particular. It's when the dispersive, the detuning, the difference of frequency between the two resonators is much greater than the coupling between them. Then there's no energy exchange. We don't exchange photons, but we can actually map information from one circuit to the other to read out, for instance, the qubits. Okay, so all this led to many papers, very many papers back in the days. So it was very difficult for cavity QED people to achieve all this, and this was done very quickly in the field of circuit QED. So this is, for instance, a strong coupling. So here you have the frequency of the cavity, if you want, so the frequency of the LC oscillator in our case, and you sweep the frequency of the other oscillator, which has just a squid to sweep the frequency, and you see a very large anti-crossing there. And you can discuss exactly what happens to the dressed state and so on. And just in a couple of years, we could see all the same physics. And I insist on the fact that this is not a simulation. It's not like a simulation, you need to do something and turn on your simulations. Here it's really like naturally the description of the system, and this is the way they behave by default. Okay, so as a conclusion for this second chapter, so we saw the normal mode description of the harmonic oscillator with these electronic photons. We saw some implementations like the lumped with the two big pads and the capacitance and the small wire for the inductance. We saw that we can hook up, if you want, a spectrum analyzer and just see, for instance, if your transmission line is impedance matched, and this is how you detect that you have a resonance at the end. We need to use some dilution refrigerator, so we'll see more pictures of dilution refrigerators in chapter 4. We described the Cooper pair box Hamiltonian in the limit EJ greater than EC, and this led us to insensitivity to a charge noise. So the voltage can have noise on it, but it does not affect the energy levels of the qubit. And this gives us a good qubit, and we can show that if it's actually coupled to a LC circuit, this gives rise to circuit quantum electrodynamics and the Jens-Cumming Hamiltonian. So, and then we can see all the spectral features that people have seen in the case of strong coupling of light and matter in these circuits. Okay, some exercises. So you can just look at the Jens-Cumming Hamiltonian. It's quite nice to look at the first eigenenergies at least. You can show the thing I skipped in the derivation, which is a b plus b dagger to the power 4 is actually this term, which is what gave us the Duffing oscillator. You can show that indeed the frequencies are, this is the F01, and this minus EC is F12 in the case of this oscillator. You can also calculate a vacuum Rabi oscillation, so the time evolution of just the interaction part of the Jens-Cumming Hamiltonian to see that the photons are exchanged between a qubit and cavity. Okay, So yeah, so I will not start the chapter 3 now, so I think that's time for the break. And feel free to ask questions. Yes?
Classically, the Duquesne oscillator gives rise to chaotic behavior. So like even though the Schrodinger equation is linear, do we still see like some quasi-chaotic behavior and useful scars on your qubits?
Yes, when they are driven with large enough powers, so a lot of photons. So now I discussed the case where there's just like at most one excitation, so it's like really a qubit. But if you drive them strong enough, you see that you really feel the complete nonlinearity, and then yes, you can have quite chaotic behavior in these circuits. It's actually a non-issue for readout. So if you read out with a lot of photons, so you plug a strong drive to your cavity mainly, but also a little bit to your qubit, which is a Duffing oscillator, and at some point you have a transition to chaotic behavior. And so quantum scars, I don't know, but I think yes, there are numerical evidences of that. Yes?
Can you talk about charge noise a little more and how it affects T1 and T2 calculus?
Yeah, so I did not introduce T1 and T2 at the moment. So charge noise is so it's there everywhere for every electronic devices. So you always have some background. It's usually known to be 1 over f or 1 over f squared, depending on the platform. And so you have a spectral density, and you have always like some fast charge noise. On top of that, you have something else which is called background charge motion. And background charge motion is the fact that you have some charges which are moving on your sample, and they just reconfigure with time, like slow, like seconds or minutes. And in that case, you have just the voltage source that I showed. The average value is oscillating because of 1 over f, okay? But it's also drifting because of the background charge motion. So if you build a qubit and it's not charge offset or charge noise insensitive, that will be a nightmare because the frequency will drift, and also because of fast fluctuation, the energy will shift in time, and this is also called, this translates into a pure dephasing if you want. So this is some T2 mechanism.
On the parallel with the security experiment,
Hmm?
so can you go back a few slides about the bootloop? Yeah, this one.
Yeah.
So here you said you scan the frequency of the resonators.
Yeah, in that case, it's the qubit.
So for an atom, I guess it's a Zeeman effect.
Hmm.
And in your case, how do you do this?
Yeah, so you saw this is so this is coming from 2 ingredients that I derived in this morning. So one of them is the fact that okay, where is it again? Yeah, we're getting back to the Duffing oscillator. So the frequency, if you want, of the qubit is this. Okay, so it's a function of EJ. And if you remember, I showed you that with a squid, so 2 junctions in parallel and an external flux. The 2 junctions in parallel with an external flux behaves effectively as 1 junction whose EJ is a function of external flux. Okay, so you build your qubit, but instead of putting 1 junction, you put 2 junctions in parallel, and then you change the external magnetic flux, and this changes the EJ, and as a result, this changes the qubit frequency. All right, so welcome back. Okay, so let's do a small recap of chapter 1 and 2. So what did we learn this morning? Yeah, so we saw the quantization of electrical circuits. So we went from the classical current and voltage. We used instead the flux and charge. We did canonical quantization to put some hats on them. Okay, and then we went to reduce units to get dimensionless phi by normalizing by the flux quanta, and dimensionless charge by normalizing by 2e. Okay, we saw that the LC circuit, okay, it has a classical Hamiltonian like this, and we can actually quantize it and then look at the eigenmodes and write it as h bar omega A dagger A. And this A and A dagger, if you apply them on the vacuum, they define what is a photon. In a photon in this oscillator, it's just that you are in the ground state. So to be in the ground state, you need to operate at very low temperature, so typically 20 milli-K. So you need to put your circuit on the base plate of a dilution refrigerator. And then you can actually excite the system and create 1, 2, 3, 4 excitations. And these excitations are quantized, and we call them photons or electronic photons. And what they are in practice is that they are oscillations of that circuit. Okay? And the circuit here has a capacitance and inductor. So if you have an oscillation, a quanta of energy in this circuit, it's like an oscillation between charge and voltage, if you want, and current in this circuit, but which is quantized. Okay. And then, what did we do? We looked at this oscillator, where we replaced the inductor by a adjacent junction. So now we have the kinetic energy, but the potential is no longer a quadratic term, it's a cosine. We switched from the n and phi to the b's operator. So this one is b dagger minus b, this one is b plus b dagger. We derived the Duffing oscillator, so harmonic oscillator plus a quartic term, b dagger, b, b. Okay, and we said, okay, these quartic terms allows us to actually have a different energy between 0 and 1 and 1 and 2. So that means that I can just operate in this manifold if I just excite and de-excite the system at that frequency without sending anything at this other frequency. And then this is just a two-level system, and I can write it as a qubit and with a Pauli operator sigma z. And the frequency of that qubit is given by the formula here, square root 8 EJEC with minus EC. So we saw that with typical capacitances, EC is like hundreds of megahertz, or a fraction of a gigahertz. EJ is like 2 to 20 gigahertz. So that gives us like a frequency between 4 and 8 gigahertz typically. And this formula is just, it looks complicated, but this is nothing else than 1 over square root LC, if you want, with the L of the junction and the C of the capacitance. And we could also derive from the Duffing oscillator the anharmonicity. And the anharmonicity is defined as the frequency of 1, 2 minus the frequency of 0, 1. And this is simply given by EC, so the value of the capacitance. And this is typically 200 megahertz. Okay? So it means that if we make the capacitance bigger, we're just going to get a smaller charging energy, and we just reduce the anharmonicity. And so then we showed that if we couple the Josephson oscillator to a LC circuit with a mutual capacitance, we get a charge operator coupling that we can write as a sigma x times a plus a dagger. And if we apply RWA, we have a Jens-Cummings Hamiltonian, and we have the exact analogy between cavity QED, so actual photons and cavities and atoms, and the circuit counterpart, which is just these two circuits coupled capacitively. Yes?
One small question. The energy diagram from 0 to 1 to the 2 state, I assume that the first gap is actually smaller than the second one, right? In reality.
This one?
Yeah.
So no, this is bigger than that.
If you would use an energy, wouldn't that excite the first to the second state?
No, so let's put some numbers. So 0 to 1, let's say this is 4 gigahertz. Okay? So we can just pick EJ and EC so that this is equal to 4. The anharmonicity is going to be minus EC. So if we take EC of 200 megahertz, this is 4 gigahertz, and this one is 3.8 gigahertz. Okay? So now if I send a pulse at 4 gigahertz exactly, I will go from 0 to 1 and back from 1 to 0, but I will not have any power spectral density at 3.8 that would cause leakage in principle, unless if my pulse is really short. So that we will see in the chapter 3. Okay? Okay, so chapter 3, quantum operations. So let's go. So the question is, okay, imagine you have these circuits. So you couple them, you build qubits, and you couple all of them together. So you want to, you call that a quantum processor, and you want to operate it. So what's a quantum algorithm that you can do? Okay. So to explain that, we use what is called quantum circuits. And quantum circuits is the following descriptions. We just put lines. Okay. So we have a qubit register with some initial states on the left. Okay. So this is qubit 1, qubit 2, and so on up to qubit n. And they have initial state 0, 1, plus, and 0. And then this is the time axis on the x-axis, and then we're going to do gates. So it means that any arbitrary quantum circuit is the following thing. We're going to do gates on, for instance, 3 qubits, on 1 qubit, which are represented as unitary, or this is a gate on n minus 3 qubits. And we're going to get measurements as well. So it means that for any line, at some point in time, I want to measure it and know whether it's in 0 or 1. And this returns a classical bit that I call M3 in this case, or M2, M1. So this looks very complicated because on the paper it looks like, okay, I need arbitrary n-qubit unitary operation and also single qubit projective measurements. This looks hard because I have to do all the n-qubit gates and so on. But, so you probably, some of you had a lecture on this maybe, but there are some theorems that are quite helping us a lot on this. So the first one is the following. If you have an n-qubit operation, actually, you can you can go to Nielsen Schwank, that's a book about quantum computation. In this book, they give you a constructive proof. Okay, so it's a proof where it actually tells you what are the unitary to apply. And this allows you to take an arbitrary unitary, decompose it into 2 qubit gates, a series of 2 qubit gates there, and a unitary acting on n-1 qubits. Okay? And that's good, because there is no n-qubit unitary anymore in this diagram. And you can repeat that on this, okay? And you repeat that. So you go from n-1 qubit unitary, you can decompose that into 2 qubit gates and n-2 qubit unitary, and so on. And in the end, the only thing that you need is 2 qubit gates and single qubit gates. And this, if you have arbitrary 2 qubit gates and single qubit gates, you can in principle play any arbitrary quantum algorithm. Actually, this is not it. You have something else which is extremely useful, which is the definition of a universal set of quantum gates. So the definition is the following. So a universal set of gates is a list of gates that you can combine in such a way that you can approximate any unitary with arbitrary precision in a reasonable number of operations. Okay? So if I give you a complicated 2 qubit gates that you don't know how to implement it, actually if you go through the math, you can decompose it on the gates that you have on the hardware if you have a universal set of gates. So the simple example of that is that if you have arbitrary X and Y gates and one maximally entangling gate like a C0 or CZ, you can get this universal set of gates and have universal control. So the goal of this chapter is to show you how we do like enough single qubit gates, one very good 2 qubit gate at least, and also a measurement on a single qubit. So here are some examples of gates. So how do you write a gate? So if you say my gate is a rotation around the x-axis, I will take the unitary, which is just the matrix exponential of minus I. Theta is the angle of rotation in the Bloch sphere, sigma x over 2. Okay. And if you have a density matrix of a qubit, it's a 2x2 matrix, and so you can write a u rho u dagger. And the u is the following for a given gate x theta. So the simplest example is when theta is equal to pi, and you have a NOT gate, so 0, 1, 1, 0, which is sigma x Pauli. So it tells you that if you're in state 0, you go to state 1. If you're in state 1, you go to state 0. Simple. You can do the same for the y-axis. You can get Hadamard. Hadamard is, you can write it as a composition of x and y, x pi, y pi over 2. You can write it as a composition of z, x, z, also with the right angles. And what it does is that it's if you start in 0, you get 0 plus 1. If you start in 1, you get 0 minus 1. So it's mapping, if you want, a 0 and 1 state to the plus and minus states in the blocks here. Okay. And for the 2 qubit gates, we're gonna get these kind of gates like the CZ gate. Okay. The CZ gate is like a diagonal 1, 1, 1, minus 1. So CZ means conditional Z. So what it does is that if the first qubit on the first line, here, which is the control qubit, is in 0, it does nothing. So it's a tensor product. So this is identity when the qubit 1 is in 0. When the qubit 1 is in 1, however, it applies like a Z rotation. So this is a Pauli Z. So it means that if the qubit 1 is in 1, it will do a pi rotation around the Z-axis. So it will turn the plus state into the minus state, for instance. Okay. C0 is the same thing. It's just that so if the control qubit is in 0, you just have identity. If the control qubit is in 1, you have a bit flip, so sigma x operator, so you go from 0 to 1. And that's the symbol for C0 gate. Okay. All clear? Okay, so let's go. So that's the outline. So we're going to look at 2-qubit control. So how do we implement single qubit gates on a transmon? We're going to look at standard calibration measurements like Rabi, energy relaxation, Ramsey oscillations. We're going to see how we tune the frequency of the transmon. So that's the question we had earlier. Then I'm going to show you an example of a 2-qubit gate. So that's not the only option, but that's an example which works well. Then we're going to discuss briefly the readout of a single qubit. So we are back to the same thing that we discussed like twice already. So we have a Duffing oscillator, and so we have a junction and a capacitance, and there's an island there in yellow. And we have a mutual capacitance to a voltage source, which is there VD. So we saw earlier that VD could be a noise, and this was a charge noise, and we saw that if we make EJ much greater than EC, we make the qubit more linear, but we also get rid of charge noise. In this example, VD will be a drive, so we're going to apply a drive on the qubit. So if you go through the derivation, and I will not do it, the Hamiltonian will be the Duffing oscillator that we saw earlier. But now we saw that if we couple two resonators like LC and the Josephson oscillator, we had a coupling charge-charge. So in that case, we're going to couple this charge to this charge. So the charge there is actually just given by the voltage there, okay? The voltage of this oscillator. So that will be just the cosine, assuming that this thing oscillates as a cosine at a given frequency omega d and phase phi. And the charge operator on this island, here we're going to write it b dagger minus b. So here I have written nothing but just charge-charge coupling. Okay? And then we go to the qubit approximation. So we replace the Duffing oscillator with just a sigma z term. And this now, b dagger minus b, we saw this is a sigma y. This is a sigma y Pauli operator. And then there's something we can do, which is to do a change of frame. So I'm not sure. So are you familiar with this change of frames? So basically, if you try, this is just like you look at the dynamics of what happens in a car. You change the frame. Okay, this is a new frame. Like here it's the same thing, but applied to the Schrödinger equation. And what's the equivalent of that is that you have a unitary, and you just sandwich your Hamiltonian with a u dagger hu. Okay. And there's an extra term which is minus I u dagger du dt. So this is, you're all familiar with this. Huh? So if you're not, I can derive it quickly. But and then, so what's the change of frame we should do? So we're going to do a boost in frequency. So a boost in frequency, it's like a sigma z is the operator associated to frequency. Okay, and we're just going to make it oscillate at the frequency of the drive. So we're going to go at we're going to displace the frame at the frequency of the drive. So we just apply the unitary exponential minus I omega d sigma z over 2. So what do we get? So if we apply this to this Hamiltonian, you see this is an exponential of sigma z. Okay, so it means that u commutes with sigma z. So if you apply u dagger sigma z u, this commutes and the u dagger u cancels out. Okay, so this part here is not affected by that. However, you get something which is minus I u dagger du dt. Okay, so du dt. Okay, I'm missing the t here. I'm sorry. Okay, so yeah, it's minus I omega d sigma z t over 2. Sorry for that. Yeah, I'm missing the t here. Okay, so if you derive with respect to time here, du dt put some minus I omega d over 2 sigma z times u, and you multiply on the left by u dagger. You just recover a term which is similar with this one, but with a prefactor which is omega d. And if you combine the two, you just get the detuning there, omega q minus omega d over 2 sigma z. Okay, and what about the sigma y term? So sigma y we can do. It's not very complicated. So it will be u dagger sigma y u with the u dagger you have to calculate explicitly from this expression. And okay, so if you do the calculation, please do it. You will get the following term. You get epsilon d over 2, so the amplitude of the drive sine phi of the phase of the drive, sigma x, and the same thing with the cosine phi sigma y. So that's very good. Why is it good? It's good because you can just adjust your parameter of the drive. So the amplitude, epsilon d, you can adjust the phase, phi, in real time. And you can adjust also the frequency, so the detuning there. So in that frame, you can do either a sigma z operation, sigma x, or sigma y operation. So you have x, y, z control of the qubit. So this is really how we do gates in practice. So this is an example. So if you just take the previous formula, you drive on resonance. So you make the drive frequency equal to the qubit frequency. You apply with a phase of minus pi over 2. You just get the driving Hamiltonian, which is epsilon d over 2 sigma x. So you rotate around the sigma x axis. And if you stop at the right time, you just get a pi over 2. If you just wait twice longer, you get a pi pulse. If you do the same thing with a phase of phi, you just get a sigma y gate. Easy. So this is really how we do gates. And so these are some more examples. So we saw the bit flip there. So you have the y gate, which is just the sigma y operator. So it's a pi rotation on the y axis. There's the z gate. So it's a pi rotation on the z axis. There's the Hadamard. Hadamard is actually a rotation around an axis which is tilted, which is 45 degrees in between the x and z. So it's mapping the z to x and the x to z. And of course, you can calculate all this, and these are unitary matrices. So if you multiply them by a global phase factor, it doesn't count because it's always enter as u dagger rho u in the dynamics. Okay, so then what do we do once we have that? We do like this standard calibration. So one of them is energy relaxation calibration. So we start with 0. We apply an x gate, so it's like a knot. So this prepares 1. And then we wait there for some time, the delta tau, and we measure and we try to, and we extract whether the qubit is in 0 or 1. So this is not like, this is from this paper, so it's like historical measurements from 2011, so the numbers are way better than like these days. But this is like what was actually measured, so it's an exponential relaxation with some voltage here, which is proportional to the sigma z operator. So you average many shots over 0, 1, 0, 1, and you get this exponential decay. And the decay here happens, and you see the time constant is about like 60 microseconds. So nowadays it's more like typically hundreds of microseconds up to milliseconds for this energy relaxation time. So is that, so can someone tell me what's the dynamics of the block vector during this evolution? What happens to the block vector? Yeah, so it depends in what frame you are, actually. So, in what frame are you? Yeah, in the lab frame, yeah. Yeah, then yes, exactly. You have a sigma z rotation, so you start. But actually, if you start in 1, you rotate like this, but you have nothing that breaks the symmetry. So you don't really have an oscillation like that. So you're like that, and you rotate on the z-axis. But so what happens then? Yeah, yeah. The block vector shrinks actually. So the block vector goes in, stays on the z-axis, goes inside the block sphere, and then goes down to the ground state. This is exactly what decoherence is doing. Decoherence is so if you have a pure set, you're on the surface of the block sphere. If you have decoherence, you actually have a block vector which is not on the surface, okay, and it's actually shrinking. So the dynamics is as follows. So you start in. So this is the x and z cut of the block sphere. So y is like this, okay? You start in 1, okay? So you're like this at the initial time, and then at a later time, you're actually going to have a block vector that shrinks exponentially, and then goes like that. And then the fate of this system is to, at a very late time, to thermalize and to go back to the ground state and like this. But there's nothing that breaks the symmetry on the z-axis, so you never really oscillate or go on the surface. Okay, the second one is the Ramsey oscillation. So here we are in 0, we do x over 2, so we are in, let's say, plus states, depending on how you define your axis. Then you have you wait for some time delta tau, and then you do x over 2 and you measure, and you see oscillations. And this is typically how we measure T2, which is like the bit flip time. So typically the bit time is also of the order of 50 or 100 microseconds. So and what's the dynamics in the blocks here in this time? Yeah?
It's to the equator,
Mm-hmm.
it was 8,
Yeah.
then you drop E outputs again,
Mm-hmm.
so it just came against the other place.
Yeah. Exactly. So now you're sensitive. Now you're really oscillating the equatorial plane, and you're sensitive to any change of frequency. So these two measurements are sensitive to very different noise sources. And so for the energy relaxation, it's typically limited by either the design, material losses. So you have superconductors, but they are covered always with some oxide. So you have intrinsic losses. You can have a spontaneous emission into the transmission line, all these things. And for the T2, it's actually effectively qubit frequency variation, so it can be flux noise, we'll talk about it. It can be charge noise that we discussed already. It can be a photon shot noise, so if you're coupled to a resonator LC circuit and the LC circuit is not really in the ground state. If it's in the ground state, it's fine. If it's some residual thermal population, it will have some T2. Okay, so this is the very standard measurements. Okay, so then what limits the performances of single qubit gates? So we saw that it's not really a qubit, it's a Duffing oscillator. So there's a second level. So what happens if we go too fast, if we make a very short pulse?
High energy, so maybe there's a chance of transition.
Yeah. Yeah, you have leakage. So basically, if you have a very short pulse in time, you have something which is very broad in frequency, and you have overlap. So again, like we discussed, 0.1 is 4 GHz, 1.2 is maybe 3.8 GHz. So the difference is about 200 megahertz. 1 over 200 megahertz is like 5 nanoseconds. So if you take a pulse which is, let's say, 1 nanosecond long, it will have some overlap with the 1-2 transition. So eventually, you will excite, do a pi pulse, let's say, between 0 and 1, but also have some leakage 1 to 2. Okay, so it means that the inverse gate time has to be much smaller than the anharmonicity here. So we cannot go faster than that. Typically, gates will be like 10 nanoseconds, and you cannot make gates like 1 nanoseconds or below that, just because of this low anharmonicity. And if you combine it with the fact that the lifetime of energy is like 100 microseconds, and T2 is also 100 microseconds, this will limit the fidelity of the gate, because it takes time to do a gate, and like quantum information lives for only a finite amount of time. So you have two possible sources of errors. One of them is control errors. So if you have a leakage, heating effect to the two states. So we are not going to consider that for the following formula. We're going to say the pulse is long enough so that we don't have leakage to the two states. And then it means that we'll be dominated by decoherence error, so the fact that we have a finite coherence time. So in practice, there's a formula for that. So I'm not going to derive it. This is just coming directly from the Lindblad equation. So if you're not familiar with Lindblad, you can just write it with the T1, T2 like jump operators. You write the dynamics of just a gate, and you will find that the fidelity is actually limited by the ratio of gate duration to the T2 and the T1 times of the qubit. And there's some numerical numbers. So in practice, if you just do the math, if you do a gate, let's say 20 nanoseconds, because your anharmonicity is only 200 megahertz, and T1, T2 is 40 microseconds, you find with this formula that the fidelity is going to be 3 nines. Yes?
Since you have the time, in the Lindbladian, what kind of factors do you take into account?
Yeah, so so in this case, okay, so there's a small trick if you want to do the calculation very quickly, so that you can apply any unitary in any possible direction and calculate the fidelity, okay? And you find actually the same thing that if you don't apply unitary, but you just look at the static evolution with decoherence starting from the 6 cardinal points of the blocks here. So you do a calculation where you start either in 0, 1, plus, minus, plus I, minus I, and you average over these possible initial states, and you look at the loss of fidelity just due to the decoherence during that time, and you will find that on average, you don't stay at the initial state that you prepared, you actually deviate from it, and if you just look at the metric of the unitary, how well do you do unitary, how well do you do how well do you do the identity operation by just waiting, starting from these 6 initial states, it's 1 minus something, and in the limit of a small error, you find this formula. And this is just take an average from the 6 initial states. And you can do a more complicated calculation where you apply like random unitaries, you average over the possible unitaries, and you find the same thing. Yeah.
May you remind, please, what was the objective
Yeah, so RAM pulses is just so now we assume here that we have calibrated the gates, and we just do that to extract T2. So in that case, it was like this was a very a measurement from very long ago, but typically like T2s up to like milliseconds have been measured. And the reason why I want to I'm showing you these two measurements because these are the two numbers here, T1 and T2, that enter the gate fidelity. And with the current state of the art, it's really very hard to be above like hundreds of microseconds. And with the anharmonicity, we are also constrained on the gate speed, and so therefore this is extremely simple. Huh? Therefore, we cannot go faster than this, and this has to be taken with respect to the coherence of the system, and this gives us immediately 3/9 of a single qubit gate fidelity. And if you look at paper, this is what everyone has. Yeah. So so now if we talk about flux control, so we saw that this qubit is a junction with a capacitor, but it's actually quite nice to be able to tune its frequency. So we did a small exercise this morning where we actually replaced the junction by two junctions in parallel, and we call that a SQUID. SQUID stands for Superconducting Quantum Interference Device. So we saw that these two junctions behave effectively as one junction where the EJ is replaced by EJ, which is a function of external flux. And this is like EJ max. EJ max is just the sum of the EJ of the two junctions times the cosine of the external flux. The external flux is the flux in this loop there. And you can introduce a flux in this loop either with a magnet or with some on-chip line where you flow a current, and just by induction you will have like some magnetic field lines that will enter this loop. Okay, so this is how we do that in practice. So usually we do that with on-chip flux lines, and by doing that we tune EJ. And I remind you that the qubit frequency is like square root 8 EJ EC. So we tune the qubit frequency. So this is what it looks like. So I took that from a paper from ETH there. So this is like yet another flavor of transmon. So this is just about the shape of the antenna. So here it's like this is a star-shaped antenna in yellow. So this is just this yellow part here, and this defines the capacitance with respect to ground, and the ground plane is like the gray part there everywhere with the small holes. And then you have a bunch of control lines that I will describe later on, which are the blue, green, red, and pink. And the green one is actually flowing a current there, very close to the small structure there that you probably cannot see. And this small structure is a SQUID with junctions which are like hundreds of nanometers by hundreds of nanometers. And this way we can tune the EJ. If you look at the qubit frequency, we get this. So typically we operate the qubit there. And the reason for that is that this is what we call a sweet spot. So at that point, if there is a tiny change of external flux, the qubit frequency doesn't change. But if we tune the flux, we're going to be in the slope. So it means that if during the tuning there is any fluctuation in the magnetic field or any fluctuation in the voltage in this line or the current in this line, this will induce a frequency change on the qubit, and this is effectively a dephasing. So this is some T2, some extra T2. Okay, so this is so now how do you couple two qubits? So I had a bunch of questions about two qubit gates. Okay, there are many ways, and I cannot tell you which one is better, so you have to try. So people have been trying this for like 10 years. What's the best coupling architecture? So the easiest one is the one I will describe. This is the direct capacitive coupling. You just take a capacitance and you couple two transmon capacitively, for instance. Of course, you can, if you make a flux qubit, so you replace the capacitance with an inductor, you can share a mutual inductance between the two of them, and then you can have a mutual inductance coupling. This works as well. You can have a tunable coupler, so you can have a qubit on the left and a qubit on the right, and you introduce an extra circuit, an extra degree of freedom in the middle. So it can be either a LC circuit, can be also something with resistant junctions, and you can do that with a bunch of capacitances. You can do that with mutual inductance with a coupler in the middle. So all this works, and all this has pros and cons. Yeah, so the cons of the coupler here is that you have an extra degree of freedom. So if I activate a gate, here I have to be careful that I don't introduce leakage by exciting the coupler. Because the coupler has a frequency, there's a LC, so 1 over square LC is a frequency, I can excite it.
What do you gain?
What do you gain? You gain that you have a, so if you place the frequency of the coupler at the right position, you can actually avoid the spurious coupling term, which are always on in this case. So and you can, for instance, also, if you want, this is like an electronic filter. Okay, So it means that if you have a qubit 1, qubit 2 at a given two different frequencies, if you bring the filter nearby, they will see each other. If the filter is like extremely low frequency, this will filter out any interaction between the two. So you have a better on-off ratio if you want. Okay, then what 2-qubit gate do you do? Okay, then it's like it's a zoo of 2-qubit gates, and they all have a name, they all have pros and cons, they all have different ways of activating. So the name is actually hard to define, so there are really many choices. There are two main approaches. Either you change the flux, so it means you introduce some current and magnetic field, or you shine some microwaves. So for instance, what IBM has been doing for a while is cross-resonance with microwave activity. What Google has been doing for a while is flux 0110, the square root I swap. And in each case, this has different technical challenges, and this gives you a different unitary that you implement in your system. And these are some citations related to that. So I will show you one example, which is the 1102 gate, which is flex activated with no coupler, so direct capacitive coupling. Okay, so I will not write equations. I will just do it by hands, and so yeah. So these are take 2 qubits and you go to tensor product. So this is tensor product qubit 1, qubit A, qubit B. So this is the computational manifold there. So you have 0, 0 state, 0, 1, 1, 0 state, and 1, 1 state. So these 4 states are computational states. And the idea is to try to use higher states, such as the 2, 0 state there, to activate to mediate an interaction between the 2 qubits. So if the 2 qubits, so these are the blocks here, if you want, of the 2 qubits. If they are in the ground state, we are in the 0, 0 state. Now, we want to do a CZ gate by changing the flux of qubit A, let's say. So what we will do is that we apply pi pulses on the 2 qubits. So let's say on qubit B, so we go there, and then qubit A, so we go there. So then I excite the 2 qubits, I'm in 1, 1. And then I will use the fact that this qubit A has a fast flux line there, so I will apply a flux in the squid, so as to change the energy levels of qubit A. And this is what you see there. And then I will try to match the 2, 0 state with the 1, 1 state. And then what do you get? What we saw earlier, just like James Cummings, you have vacuum Rabi oscillation between the 2 states. So it means that actually these states become a doublet, and you have an exchange of excitation between the two. So the state that was, the population that was in 1, 1 will go to the 2, 0 state, and then it will come back to the 1, 1 state. Okay, so if you look at what happened to the states, so think about computational states. So if you're in 0, 0, essentially 0, 0 goes to 0, 0, nothing happens. 0, 1, same thing. 1, 0, same thing. So there's nothing. But if you're in 1, 1, you go to 2, 0, and you come back to 1, 1. So it means that in this manifold, these are 2 states. So you can think of this as a qubit if you want. This is like 2 states. You do a 2-pi rotation in this manifold. And then this adds a global pi phase. So are you all aware of this? So what happens to a qubit if you do a 2-pi rotation? No? Yes? Yeah, you have a minus sign. So, I mean, this is not very difficult to derive, but if you do a complete pi rotation, you get a global phase on the wave function of the qubit, which is just a minus sign. Usually you don't care, you discard it because it's a global phase. But actually, if you have multiple systems, you do care, because you will acquire a minus sign on this manifold, on these 2 states, but these other states, they don't acquire this minus sign. Okay. So that's what we're doing. So we do a 2-pi rotation in this manifold. So we imprint a minus sign on these two states, but the other ones, they don't get any phase. So the 1, 1 goes to 2, 0, and then comes back to 1, 1 with the minus phase. So if you write it in the basis 0, 0, 0, 1, 1, 0, 1, 1, what you get is 1, 1, 1, minus 1, and I told you it's a CZ gate by definition. And typically the fidelity is about 2 nines. Yeah. And the reason for that is that, okay, I can discuss it in more details if you want, but you have the gate speed that matters, you have the on-off ratio, you have the fact that you can have a leftover population in the 2, 0 states that can be considered as leakage as well, and all this combined give you typical fidelity of 2.9. Okay, so the question is, what can you do with the CZ gate? So, what can you do with the CZ gate? Yeah.
Single qubit rotation
Yes. Yeah. So, so for instance, this is a paper from Google from 2014. So what they did there back then is that they had a linear chain of 5 qubits, and so they had calibrated their CZ gate. It's not exactly the one I showed you, but very close. And then they also had a single qubit rotation, but they will just use some of them, and they will do a GHZ state. So what is a GHZ state? It's just like a generalized version of the Bell states. So if you just have 2 qubits, the GHZ state for 2 qubits is a Bell state. So it means 0, 0 plus 1, 1 over square root of 2. If you have 3 qubits, it's 0, 0, 0 plus 1, 1, 1 over square root of 2, and so on. So for n qubit, it's 0 n times plus 1 n times over square root of 2. And if you want, we can, this is very easy to see that these circuits, y over 2 minus y over 2, CZ y over 2 is generating a Bell state. So if you want, we can do it. We can do it quickly. So we start in 0, 0 there. So what is the state at that point? What's the state here? You apply the plus y over 2 on one qubit and minus y over 2 on the other qubit. So you rotate around, so you start in 0, you rotate around the y-axis. So plus y over 2, what does it do? No, it's not Hadamard. Hadamard, we saw it's a combination of y and x. Yeah, it's just purely y. So it's really purely a rotation along y-axis. So what's the state there? So y over 2 on 0, it's what state is it? No, so y over 2 on 0, it's like you're doing a pi over 2 rotation starting from the 0 state. So you're for instance, depending how you define your axis, you can say it's a state plus, okay? So here you're in state plus. So if you do, so if this is state plus here, if you do minus y over 2, what's the state there? Minus. Okay. So you start in 0 tensor 0. Here you have plus tensor minus. Okay. So what does CZ does to plus tensor minus? Yeah. So we saw an example. We saw that. So here we are in the state. We are in the state plus tensor minus. Okay. Plus tensor minus, it's a 0 tensor minus plus 1 tensor minus over square root of 2, okay? And we saw that CZ means that we're going to flip the phase of the second qubit if and only if the control qubit is in 1, okay? So if you're in 0, we don't flip the phase. If you're in 1, you do flip the phase. So it means that this becomes, so this is 0 tensor minus, and the other one is what? Yes, 1 plus. So okay, so it's like a CZ. Now we're applying CZ, 1 plus. 1 plus, okay. And then what do? We do y over 2 on the second qubit, plus y over 2 on the second qubit. What does that do? So from state minus, so we saw that plus over 2, plus y over 2 starting from 0 create plus, minus y over 2 create minus. And then, so if we apply plus y over 2 on the minus states, we are undoing the evolution of the minus y over 2, right? So it means that the minus state comes back to the 0 state. So this one becomes 0, and the plus is actually 1. Yeah. So this goes to 0, 0, plus 1, 1, which is a Bell state. So you see, so this is really easy to see, and this is really easy to read this thing. Okay, so this, and then they can do the tomography and see that this is indeed the Bell state. And then they can continue this protocol. You just have to apply this minus y over 2, CZ minus y over 2. You get the GHZ state with 3 qubits, and so on. And you quickly see that it's actually, so it's a process tomography matrix, so it's a very big matrix. It's like D squared dimension for Hilbert space of dimension D. So this becomes really, really big. And what you see is that in that paper, they had a CZ gate of about 2 nines fidelity. So they could generate a Bell state with 99.5%, which is essentially limited by the fidelity of 2 qubit gates. So single qubit gates are 3 nines, so we can just ignore them. So this is a 3 9, 3 9, 3 nines, and we are just limited by the fidelity of the 2 qubit gates. So typically, if we want to talk about fidelity of algorithm, we need to talk about how many 2 qubit gates we have. And here we just have two nines. And now you see that it's actually scaling very poorly in the number of qubits and number of gates, because now you have 96%, 86%, and 81% on just already 5 qubits. So you see that, just to tell you, just to give you an idea, with 2 nines of 2 qubit gate fidelity, this is the fidelity you will see if you generate a maximally entangled state in a quantum processor. And this is what it is. It's like 80%. Okay, now the missing part is also the readout. Okay, so earlier we saw that we can couple to a LC circuit. The LC circuit we can probe it through a transmission line. We get a reflection coefficient. We see whether we can see the impedance of the circuit if you want, and we see whether we are on the left or on the right of the resonance frequency of that circuit. So here you can really see the analogy as so if we take the Hamiltonian that we saw earlier, and we apply, so I will not do it again, but these are the maths behind that. It's second order perturbation theory. Sometimes it's called the Schrieffer-Wolff transformation, which is more or less giving the same, it's exactly giving the same result. So we apply a change of frame with the unitary, which is just the interaction term in the James-Cumming Hamiltonian. And if we do that to second order in G over delta, so we try to make delta big, much bigger than G, so this is what we call dispersive regime earlier. We end up with the following Hamiltonian. We have a qubit, their sigma z term, with a qubit frequency, which is renormalized by the coupling. Okay, so the qubit frequency is slightly modified. And we have the cavity, cavity frequency, which is renormalized by a term that depends on the state of the qubit. So it means that if you probe this cavity in transmission, so in practice it's usually an LC circuit, you see a peak of transmission when you are on resonance, and the peak on transmission will be either this peak or that peak, because this is the frequency axis there. The frequency is shifted depending on the state of the qubit, whether your sigma z is -1 or +1. So in practice, we typically detect the phase. So for instance, if you operate at that point here, you will see that your signal, reflected signal or transmitted signal, will require a phase shift which is either positive or negative depending on the state of the qubit. So if you combine that with the right amplifiers, it's just like a scattering matrix measurement. You just send a pulse and look at the phase of the outgoing pulse. You can achieve a projective measurement on the qubit. And if you take the analogy with the cavity QED, it's like as if you had an actual cavity with a medium in there, which has a refractive index which is either below or above 1. This is actually the qubit, and this is effectively changing the frequency of the cavity. So in practice, if you look at the state of the art, so this is what people do in the state of the art. So these are a schematic for oscillators. So down there you have the qubit, okay? There's a capacitance, and then we have a readout resonator. And it's not coupled to the transmission line, it's actually coupled to yet another circuit, which is called the Purcell filter. So it's like a filtering circuit, which is just the same thing than the readout resonator, but with a larger coupling to the transmission line. And we also make the transmission line asymmetric with the capacitance there, so as to make sure that if you have a photon in the resonator, it will be filtered through that filter, and will preferentially go to the output port rather than the input port. So all this is like a circuit optimization, like these are people like drawing circuits like the one we discussed today with 3 modes, and they try to optimize the parameter, the coupling capacitances, and all this to just get the right parameters and the right coupling to get the optimal readout. And there in the output port, you can put a quantum limited parametric amplifier like the thing we discussed in the introduction. And in the end, what people have is typically readout errors of below 1%, fraction of a percent. So fidelity of 2 nines, hardly 3 nines. It's really hard to push on the fidelity of readout. And one of the reasons is also the chaotic behavior of the qubit if we drive with too many photons. And we get a readout duration of typically 100 nanoseconds with a few photons and SNR of like few tens. So this is just to summarize. We have single qubit gate 3 nines, 2 qubit gates about 2 nines, difficult to get 3 nines. And the readout is typically 2 nines if you optimize the architecture.
Just one question.
Yeah.
You go to the Google paper.
Yeah.
Can you just the X and Y? Can you
Here and there.
write more on them and how they are related?
Okay. So this is actually this is actually a process tomography matrix. So it means that they apply this unitary there, okay, and they want to know what they generate, yeah. So okay, how should I introduce? It's not so easy to introduce. It's a way to represent the unitary that they have. So they need to do the tomography of the unitary. So it means that they insert multiple initial states 0, 0, 0, 1, 1, 0, 1, 1 there, and they look at what comes out, and they detect either 0, 0, 0, 1, 1, 0, 1, 1. And then they look at the correlation between the input state here, let's say 0, 0, with the output state. So if they inject 0, 0, they get either 0, 0, or 1, 1. That's a Bell state. Yeah. And this is actually showing you that this process, this unitary is really generating a Bell state.
So even if they input 1, 1, they can see the 0, 0?
Yeah, because if you redo the math, this will generate a Bell state with. Yeah. 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 So yeah, exactly. So that's the architecture which is working the best at the moment. It's just that you have this chain of three circuits: the qubit and a resonator and a filter, and you just copy paste that, and you put multiple ones successively in the same feed line here, and you make sure that the resonator frequencies are separated by a few hundreds of megahertz. And then, depending on the frequency that you send with your electronics, you read out a different qubit, basically. Okay, so so conclusion, we saw that we need a universal set of gates. We can get single and two qubit gates. We can get actually X, Y, and Z control on single qubit gates on a transmor. There are bit flips and phase flips, so I did not discuss them a lot and what's the source of them, but this can be like any source of noise, so charge noise, flux noise. For phase flip, bit flips is mostly energy relaxation, and this limits the fidelity of gates because the speed is constrained mostly by the anharmonicity for single qubit gates. There are many different coupling schemes, and there's a huge body of literature on that. So we saw the example of a CZ gate where we try to match the energy of a 2-0 state with the 1-1 state in a 2-qubit subspace. And then we do a 2-pi rotation on that, and this gives us a minus sign on the 1-1 state. And you can use that to generate GHZ states. And you see that the fidelity scales not so great with the number of qubits. Okay, so the readout is made by coupling the qubit to a LC circuit, and the frequency of the LC circuit, with perturbation theory, depends on the state of the qubit. And we can implement a single shot readout actually on this just by sending a micro F pulse there and reading it out. And we can do some improvement with parametric filters, with Purcell filters, with a parametric amplifier, and so on. Okay, so exercises. So there's the small thing we discussed. So if a psi goes to a different frame, and now it's a psi prime, and the change of frame is u, show that, okay, the transformation is what we discussed, so u dagger hu minus I u dagger du dt. So calculate the Lindblad evolution if you apply a gate around, let's say, y, with an operator which is dephasing, so square root gamma phi sigma z. And what's the decay rate of Rabi oscillation? So this is one of the plots that we saw with Rabi oscillation. Yeah, so that's actually what we did. How to generate a Bell state with a single qubit gates and CZ. And then we discussed the fact that we can generate any n qubit gates with single and two qubit gates, so you can take a matrix and decompose that on the gates you have in the hardware. Oh, good. Any question? Okay, now we saw qubits, we saw LCA circuits, we saw how to operate them. We're going to try to build a quantum computer. So let's go. So this is a picture of a chip. So this is really how it looks like. So the scale bar is like 1 millimeter there. So this chip is from ETH, Andreas Wallraff. So I was a postdoc there like 2 years ago. So that's why I'm showing you this example. So this is more or less the state of the art in Europe at the moment in terms of complexity. There's like so this one is a 17 qubit chip. There's a 25 qubit chips in Chalmers at the moment in Sweden. There's also a 17 qubit chip in QTech in Netherlands. But this is about like the best that you can find in Europe at the moment. So what do you see? It's a lot of structures now and a lot of wires. So the first thing you see is that the yellow things, so this is like the capacitances of the qubits. So these are the star bonds we saw earlier. So all these yellow islands, they are metals and they are not connected to and the rest is the ground plane, and they are not connected. Actually, there's space everywhere there, and they just act as a capacitance between the metal there and the ground plane. Actually, so there's something I did not describe a lot, is that to do single qubit gates, we need to drive with a voltage, okay? And so this is what we call charge lines in pink there. So we put a voltage source there, okay? This is a transmission line, and there this comes as an open close to the qubit. So this is like a capacitance to the qubit island, and this is how we drive single qubit gates. We do X and Y rotations. Then this is something I described more in detail. So we have flux lines, so these are the green lines, where we flow a current, and this current can be varied at the nanosecond level, as nanosecond time scales, and we can vary the qubit frequency very, very fast like this. And then, so these qubits are coupled. In that case, they are coupled with a coupler. So it's not like the direct capacitive coupling I showed you, but the coupler is actually just a resonator, which is at very high frequency. So from the viewpoint of the qubit, at the qubit frequency, it's essentially more or less like a capacitance. And we have the readout architecture. So here, in that case, there's a readout resonator with a Purcell filter, which is also on the resonator. And this is the answer to the question, to your question. So what happens if you want to read out multiple qubits? Well, you have this feed line there, and then you couple to first qubit, a second qubit, and so on. And depending on the frequency, which is more or less the length of this resonator, you address or you read out one qubit or the other. Okay, so it's simple. Yeah.
Why are some qubits like some are like star-shaped and like other ones are like star-shaped but like with a bigger notch? So like what's the difference for like the readout? Like why do we need like more space for the readout for like one qubit or another?
Yeah. So indeed, so these qubits, they don't actually operate at the same frequency. So this is for a quantum error correction experiment in this chip. So you see that there are two types of qubits. There are the ones with the big islands, like this one, this one, this one, this one. And this one, and you have the one with the small island, like this, that, and that. So the one with the small island, they have a smaller charging energy, and also they have a larger coupling to the readout resonator. And the reason for that is that these ones, they are actually called ancilla qubits. So we're gonna encode a logical qubit in these sets of qubits, and these ones are being used to extract information about errors. So we do a lot of measurements on them, so we want to couple them a lot on readout to have efficient readout.
The geometry of the qubits was chosen because of convenience or just?
Yeah, so there are many things. So here it's actually an optimization. So the circular shape there is first of all, it's really not unique. So some people have very different looking qubits. But the fact that this is circular allows you to put like wires coming from all directions, and there's no like asymmetric design where you actually cannot couple from anywhere in 2D. And then there's some optimization on how small the capacitance is, because if you make the capacitance too small, you constrain the electrical field becomes bigger. And then if you have any leftover, let's say lossy materials like oxide in the gap of your capacitance, you suffer more from losses. So you want big qubits, but you want to scale, so you want small qubits. So you need to trade off and you need to optimize the geometry of the capacitance. So we do that in practice with a finite element solver, and this is electromagnetic simulation at a gigahertz frequency, and we optimize for participation ratio of interfaces. Okay, all good. So, and then if you look at the chip there, okay, the T1, T2, so now it's significantly better. These numbers are from a couple of years ago, but it was about 40 microseconds, so this is what I told you. Single qubit error is like 0.1%, so it's 3 nines, this is what I told you. 2 qubit gate error on average is 1.5%, so about 2 nines. And then readout error is like, about 2 nines. Huh? So this is more or less the performances I told you. Okay, so this is what it looks like. So this is something you can really hold in your hand. This is the sample holder. Here you have a PCB that is, and the connectors there. So these are SMP connectors. So we can just connect wires to all these connectors to go to the fridge. And then it's a multi-layer PCB. So these signals are routed through different layers of the PCB to go on the chip. And then you have actually like wire connection to the ground, to the different metallic part of the chip. And the chip I showed you is there. Okay. Yeah.
In the previous slide, it seems to me that
Yeah, yeah. So this is actually a big problem in this chip. So everything I showed you is 2D. Yeah. So it's really planar architecture. And indeed, if you have a planar architecture, but you have more than just two lines of qubit, like a ladder. If you have really a 2D structure, you have to make some wire crosses. So this is a charge line, and it's crossing the couplers of these 2 qubits and these 2 qubits there. So if you drive and also this one. So if you drive, actually you see it in the chip. If you drive a single qubit gate there on this qubit, it will also drive a bit this one, this one, this one, this one. So you have crosstalks. So you need to calibrate for crosstalks, and you will see that. So we do a crosstalk matrix measurements, and you need to compensate that. So in practice, what they do is that when they drive this qubit for single qubit gates, they drive also a little bit all these other qubits to compensate for the leakage, and they do some destructive interferences to just not drive the other qubits. Okay, yeah. Yeah, so exactly. So this is like this is from a couple of years ago. Now they do, at the moment they do a 3D integration. So they do a what they call flip chip architecture. So they do a qubit on one chip. They do all the wires and resonator on the other chip, and then they glue them together. They just take the 2 chips and they just put one on top of each other. They solder them together with indium, which is a good superconductor. And then this is like a structure with 2 chips. And this is also why on the Google paper, they also use this technique. You only see the back side of a chip, so they can show you the chip, but it's just like the wrong side, because there are 2 chips and they are just facing each other. Yeah, so you have to be very careful on how you do that. So you have to align the 2 chips carefully. And then you have to, if you have a big processor, you need space. And you have to be really careful about the tilt angle between the 2 chips when you solder. Because if you have a very small tilt angle, at some position, the coupling, the distance between the 2 chips will be less than at other position, which means that the capacitances between the 2 chips will be not the same value depending on where you are on the chip. So you have to really calibrate. And this is a lot of engineering to scale up. Yeah. And then you have also other kind of 3D integration, like what IBM has developed, and also the recent things at Lincoln Lab at MIT. They do 3D integration in the chip. So they actually grow the chip, and they do multiple layers, and then they grow a substrate on top of that, and they do their qubit on top of that. So it's really like 4 or 5 layers of wires. Okay, so this is the packaging of this. Yeah. In the flip chip architecture? Well, this is the same. So you're not gonna get you're never gonna get your chip closer than about this distance if you want. So like, yeah. So it means that the smaller distances are always within one chip. So I mean, there's a trade-off obviously, but you're not gonna concentrate too much electrical field between the 2 chips. So as long as you don't touch, it's okay. But it's really about reproducibility and how good you are at really making the two things really parallel. Okay, then you take the sample holder. This is a SMP bullets, and you put it in the fridge. So these are coax cables to SMP. It goes there. You put in, so that's a blue force fridge. So it's like a similar fridge than what I showed you earlier. But now here you have multiple pulse tubes. So on that fridge. Yeah, this is the 4K stage, and then this is the base at about 10 milli-K, and these are the cans with the magnetic shield and the samples inside. And of course, you see that if you want to start to control like tens of qubits, you need many controlled wires. So there are also people working on how to make that compact and how to have thousands of lines and not just like struggle a lot to have like this fridge has 200 lines, something like this. And of course, you need all that, like a lot of control electronics. So how do you control this? Well, you need microwave sources, which are like at several gigahertz. You need to generate fast pulses at the nanosecond level to just shape your waves. So you have arbitrary waveform generators. So these guys are arbitrary waveform generators. And then you mix the signals of the arbitrary waveform generators with the sources to just generate the qubit pulses. And this is how you generate all your gates. And so it's so this is a lot of instruments, a lot of money, but this is essentially 2 electronic racks. So it's not like gigantic for 17 qubits. Okay, and then the wiring diagram, this is what it looks like. Okay, we can discuss in more details, but maybe this is too. This is a lot of microengineering. Yeah, and this is what it looks like, all the electronics and all the wires, and all this goes to the fridge. So also there's a lot of work and development with companies on fast electronics. So these boards there, they are inside their FPGA, field programmable gate arrays cards, which are very fast boards, and they're actually it's quite involved to. It's really an art to be able to code them and develop this electronics. So. And then what you can run some calibration algorithm, you can look at the data, and if you're an academics, you find all these tables. So the industrial groups don't show that, but in the academics lab, you get all the parameters of all the qubits. So it's a lot of calibration, you see. It's like maybe 24 hours of calibration at first before you can do anything. And then you have this kind of diagram. So this is a layout of 17 qubits. On each qubit, there's a circle, and then you have the single qubit gate error. So you see that this one has more error than this one. So you can really see that the errors are not the same everywhere. And on the link, you have the blue link. You have the 2 qubit gate error. And what you typically have is that, for instance, here on this link, you have one very bad qubit gate, or 2 qubit gates. So this one has 95%. This one has 97%. So then if you run an algorithm, you need to compile it, taking into account that some of the gates you want to avoid because they are much worse than others. So there's also some compiling things involved. And then if you look at the T1 or T2, well, this is again what I told you. You have tens of microseconds. The single qubit gate fidelity is 3 nines. 2 qubit gate is 2 nines. The optimized readout and so on. Yeah. And this is the question you asked. What about crosstalks? Well, you do this. So it means you drive Rabi on qubit I, and you read out all the qubits. And you see that qubit I is indeed oscillating, but older qubits are also a bit oscillating very slowly. So you see that you have this diagonal there, and off-diagonal elements is what you don't want. And they are like crosstalks. Yeah. Yeah, so single qubit gates are more or less limited by their speed. As I told you, it's like the anharmonicity versus the coherence time. So if you improve the coherence time, either by better design of the structures or better fabrication, you're just going to get better single qubit gate fidelities. That's one thing, but this is not the limiting factor, because you see there's another of magnitude worse error for 2 qubit gates. So usually we focus on 2 qubit gates. And 2 qubit gates, in that case, they are limited by the fact that we activate them by flux tuning the qubits, as I showed you. And when you flux tune the qubit, you change the qubit frequency a lot. Okay? And the qubit frequency can dephase, so this creates T2 because you have flux noise, but also there are spurious two-level defects, what we call them two-level defects in the circuit. So they are typically stored in the oxide, and they can take some of the energy of the qubit as you cross them. So this is a non-issue. So Josephson junctions are 2 metal parts, and in between you have aluminum oxide, and in this aluminum oxide you have very strong electrical fields. And this material is an amorphous oxide, so it has no real structure, and you can have like oxygen or like a free dangling bonds and all the nasty things you can think of in an oxide, which are not clean. And eventually this is cold, and this can behave quantum mechanically. And if you apply a large electrical field because you're using your qubit, you may eventually lose energy to them. And so when we sweep the frequency, actually we cross through the resonant frequency of these defects. And this is actually the major limitation. It's like these gates are really bad, not by design or not by fabrication, because this one has a really bad defects nearby. It's an active, there's a lot of papers, a lot of people working on that, and that's a limitation for this group for a while. This was the limitation for Google. This is also why Google has been using flux-activated couplers, because then the coupler crosses the defect, but not the qubit. They try to not flux tune the qubit because of that. This is also, I think, why IBM came up with microwave activated gates. They don't want to change flux because they want to avoid them. And this, okay, so yeah, so you get this crosstalk, and then you give that to your software, and the software does the right thing to drive all the qubits. When he wants to drive one qubit, it's actually driving multiple qubits, one very strongly, and all the others to cancel out the leakage through the others. You can do the same thing with flux. So this is the green map here with flux. If you apply flux to one qubit, what happens? If I show you the chip again, yeah. So for instance, imagine I apply flux to this qubit there. Sorry, the green line there. Okay. So I will flow a current in this line. Okay. And then it's shorted to ground there, so it goes to the ground there. And then the current has to escape the chip. So the recirculation current will go like this. Okay. Eventually, it will have to cross and go there. Okay. Or it will go like this. So where does the current recirculation current flows in the ground plane? It's actually hard to predict. And if it goes like this, you see that it will actually go close to this qubit. So this we have a flux line, and they are shorted to ground, and in the ground plane the current recirculates, and it's actually going close to the other qubits. So if we apply flux to qubit I, what we see is that we're actually fluxioning all the other qubits a bit. So what do? Well, we take that into account, we compensate for that, and we then redo it again, and we see that the matrix is much better because we have to calibrate the crosstalks. Okay, so it's difficult. Yeah, it's difficult. And so just a bit, so I will not describe the experiment of that chip because it's quite involved. It was a surface code experiment, distance 3, so it's 17 qubits, 9 qubits for storage of information, and the rest to extract syndromes. But just to give you an idea of quantum error correction, so if you're not familiar with that, so the idea is to protect information with by encoding that in multiple qubits. So in classical, you have registers of n bits, okay? And instead of using one bit, which is either 0 or 1, you just copy it. So you have 0 many times, okay? You have 1 many times, okay? And then eventually you will get one error. So 0 will go to 1 or 1 to 0. But you can detect it because you have the same copy many times. So if just one is faulty, you just do a majority vote, and you know whether your register is in 0 or if it's in 1. In quantum, while you have the non-cloning theorem, so it's a little bit annoying because you cannot just copy your bit into a register. So that's a quote from John Preskill. So you cannot. But so what you can do is to you can encode the qubit in a correlated state of many qubits. So for instance, if you do you have the equivalent of this bit flip code here, where you have 0 in all qubits if the qubit is the logical qubit is in 0, 1 if it's in 1, and the plus state is actually a superposition of all qubits entangled together. And so this we call logical qubit. If we can achieve that, so for bit flips or phase flip, it was done. But then when doing gates remains to be done because you need to do fault tolerant operation, which means that you are doing gates on this logical qubit without breaking the protection, otherwise it's useless. And there's a theorem that tells you that every code has a fidelity threshold, which means that you have to do all the operation better than something for the code to work. Okay? So you have a faulty system with bit flip and phase flips, and now what you will do is you're going to make an even bigger system. So you will have more bit flip and phase flips. So that looks worse, unless if you do some encoding and you try to correct for errors. And that works as you scale only if all the fidelities of, let's say, gates you need, readouts you need is better than a given number, which is called the threshold. Okay. So like this is okay. This one is again a Google paper from 2021 where they did the bit flip code in that case, I think. Yeah. So you see they take a chain of qubits like this. So the gray ones are the data qubits, and the black ones are called the measure qubits or ancilla qubits. And so what do they do? They say that if we are logical 0, all the gray ones are in 0. If it's 1, it's all 1 everywhere. If it's a plus state, it's 0 everywhere plus 1 everywhere. So it's untangled. And then if you want to know whether this qubit there was faulty, what do? You do the following. You have a qubit I, and you take an ancilla there, and you do a majority vote with the neighboring qubits. So you do a C naught there and C naught there. So if this one is in 0, and the ancilla starts in 0, and this one is in 0, the C naught will actually not do anything because the control is in 0, and same there, so the ancilla remains in 0. If this one is in 1 and the ancilla is in 0, this will flip the ancilla to 1, but if this one is in 1 as well, this will flip back the ancilla to 0. So it means you will still measure 0. So if there is no problem, you just measure, you keep measuring your ancilla, and this is what we call a cycle of quantum error correction. So you do that on all the measured qubits at the same time, all the time. And as long as you do that and you only find all the ancillas in 0, there is no error. But as soon as you start to find an ancilla in 1, it tells you that, okay, either qubit I or qubit I plus 1 is flipped. And since you have I plus 1 and I plus 2, and also I minus 1 and I, you can tell who flipped and then flip it back. So that's the idea of quantum error correction. So they did that with different distances. So distances is basically the number of data qubits they use. So with 5 qubits up to 21 qubits, and what they saw is that if you do that all the time, so you measure extract errors all the time, with 5 qubits, the logical error per round of error correction is like this. The threshold is the dashed line. And as you increase the number of qubits, so you scale, it's actually exponentially suppressed. So for a bit flip, it looks like it works.
How is this process repeated if after you measure the ancilla, the state of that qubit collapses? So do you have to re-prepare it every time? Or?
No. So actually, so what you measure is the ancilla qubits, not the data qubits. So the data qubits are maybe entangled. You don't know about it. You don't want to know about that. But what you measure is like you do C naught with an ancilla, and the ancilla you measure, okay? The ancilla, if you find it in 0, you do nothing, and you just repeat, go to the next round. If you find the ancilla in 1, depending on the list of results of all the ancilla, you know what data qubit to flip back. So you apply a knot on the right data qubit, and you reinitialize the ancilla before starting the next round.
Doesn't this measurement-based conditions induces some non-linearity in the system?
So I'm not sure what you mean by non-linearity, but so indeed, so if you do that whenever you do a gate, imagine that you're fluxioning the data qubit, and the data qubit, when you fluxion it, it's actually exposed to dephasing. Then every time you do a gate, you have a finite fidelity, so you can the gate itself, the C naught gate there, can introduce errors to the data qubit. So I'm not sure if this is what you want to say, but whenever you do this round of correction, if you do them too often, since 2 qubit gates are not great, you can introduce more errors on the data. Yeah.
So around in this sense is a measurement?
A round is that you do C naught. You do all, basically what you do is operations in parallel. So in that case, what they did is that they did C naught there, 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 all this in parallel. Okay. So every other link they do a C naught, and then they do C naught on the other link, like this one and this one and this one, because they cannot do C naught on 2 qubits at the same time. So they do the first C naught and the second C naught on all the qubits in parallel, and then they measure all the ancilla in parallel, and this is one round.
So like how strongly entangled are the ancilla qubits to the qubits we want to get the information from? Like, you know, if we're getting information from the ancilla, instead, you know,
so this is how you design a quantum error correction code. So here, what you extract is the expectation value. So okay. So maybe I should. You start in 0 there, and you flip it, this ancilla, only if the first qubit is excited, and you flip it again only if the second qubit is excited. Okay. So overall, what you measure is Zi plus 1 expectation value. So the measurement operator is Zi plus 1. Okay? And then you take the expectation value of this, okay? Sigma Zi I plus 1. This is like called the joint parity, okay? And this thing does not harm the qubit if the qubit is entangled. Yeah?
since you have like, for example, like, C naughts don't necessarily give entanglement, but like they can. The thing is like I and I plus 1 are like coupled to the ancilla, so like the whole system is like a single ket. So
Yeah, so
measure the ancilla, but you actually can't affect the
Yeah, but this is part of the design of the code. So it means that the code with this logical, so it's called logical code words. Okay, it's called the stabilizer formalism. So basically, the fact that you use 0 logical as a list of 0 and 1 logical as a list of 1, and you can have any superposition of 0 logical and 1 logical, and also you can measure sigma zi plus 1 for all I is not incompatible, and this doesn't create dephasing on the logical qubit. So that's how you build this code, and actually this is very simple, because imagine that you are in a logical 0, sigma zi plus 1, or in 1, it doesn't tell you any information about whether you're in 0 and 1, because the result of this, if you're in the logical subspace, should always be 0. So you see that the joint priority is always 0 in principle if you're either in these states or a superposition of these states. So there was a, yeah. Yeah, so that chip I don't know, because it's made from a company, so I don't have the parameters. I don't have any, yeah.
Okay, but if that would be the case, then the ancillary qubits wouldn't they be the most prone to errors? Like,
Yeah, usually, yeah.
so then how do you know that you can rely on, if you measure one, that it was actually because of the fact that on the logical?
Yeah, so usually, so this is a good question. So indeed, your ancilla can have, let's say, a bit flip in the middle of this sequence, and maybe you detect a false syndrome there because you think that you have a bit flip somewhere. So, and maybe you will correct an error that does not exist. But then what happens is that the next round of measurements, if you correct an error that doesn't exist and you don't have this same error on the ancilla, then you will see that actually you did something bad and you will correct for it. So as part of multiple rounds in series, if you have the right frequency of rounds of error correction, that should not be an issue. Okay. So this works, and this works for 1D code. So basically, when you have a 1D code, you correct for 1 error at most. So it works. You can either correct for bit flips or phase flips. But if you want a quantum computer, you have to correct for both. And this is typically why people do surface code. And surface code is way more difficult because the threshold is way more difficult to achieve. And also, you have more qubits to control, and it's really hard to scale. So, so that's a yeah. So you need the surface code or some equivalent code which is 2D. So the thing I showed you, the initial processor is from this paper there with 17 qubits. They had 3% error per cycle, and the cycle was 1.1 microsecond. And this is not sufficient to make the logical qubit much better than physical components. Yes?
Slide previous slide, so the graph, as I can see, as we increase the number of qubits, we have a less logical error probability.
Yeah.
That's the idea behind
Yeah. So in an ideal world, so that's the threshold theorem. If you do things better than the threshold, then as you you scale the system size, go to the thermodynamics limit, you have more degrees of freedom, but the overall thing, the logical qubit that you build out of that should be better and better with the system size.
Okay, but where is the problem here? So,
But the problem.
hard to increase the number of qubits.
No, so in that case, it's easy because they are just correcting like bit flips or phase flips. But if you correct the two at the same time, no one did better than distance 3. So distance 3 is the numbers I'm showing you now, 17 qubits. Actually, no, sorry. Actually, Google this distance 5, but they were not much better. So distance 5 is 49 qubits. So it starts to be like really a lot of qubits very quickly. This is the amount of error you get per cycle, and this is actually not great, because if you think about it this way, this is like a 3% error every 1 microsecond, so you can calculate that as an effective T1, T2 logical, and this is not better than physical components. And even with distance 5, it was not really better. So the issue there is that if we are too close to threshold. So it means that maybe they are just a little bit below or a little bit above threshold, but if you're very close to threshold, how does it scale with number of qubits? It's exponential. So if you're too close to the threshold, you're not going to need something like 10 to the 6, 10 to the 8 qubits to build one good, maybe 10 to the 4, 10 to the 6 to build one good logical qubits. And then you need about like 100 logical qubits to do useful applications. So you need about 10 to the 8 qubits physical to do something useful. So that's quite depressing. So that's why you need better fidelities to begin with to be able to do something that scales with like a much smaller number of qubits. But this is exponential. Yeah, so.
So ETS experiment.
Yeah.
You post select and you load all readouts. So
Yeah.
in the other collection experiment. But then the Google one doesn't do that. They don't post-select, they keep leakage errors. So then how do you compare those two stats?
Yeah. Okay. Yeah. So indeed, like this. Okay. So this experiment is cheating because what they do is that whenever they detect whether there's a leakage or not in their correction cycles, and usually sometimes the 2-qubit gates or the readout can induce leakage to 2 states. And if they see this event, they just throw away the data. Okay, and they say that we need to correct for that, but assuming that we correct for that, we should have the same result if we throw away the data or if we correct perfectly. So they do say that in the paper, which is, you can say whether it's fair or not. So they are cheating on that point. They are cheating on another point, which is that in that case, they just don't correct errors. So they detect where errors happened, and they correct the logical code words, so the logical states, based on what's the history of errors, but they don't actually correct them by applying pulses. And in the Google experiment, yeah, they have a different architecture, so they don't do this. They don't post-select on leakage, but they actually do the same thing of cheating. They don't correct fully for errors. They actually update their frame. So they say that if so if you have, let's say, 3 qubit, 0, 0, 0 to be your logical 0, if you see qubit 2 flipping, then you say, instead of flipping it back with a pulse, they say, now my logical, from now on, my logical 0 is going to be 0, 1, 0. And you can do that. But this is this won't work for practical application, but this is how they do it.
And also when they do simulations to benchmark their experiments, the noise models that they use are all different. So when you're comparing the Google paper and the ETH paper, when you're talking about state of the art, how do you?
Yeah, so state of the art is really what is measured. So it's like an error cycle with a duration and then a percentage of error per error cycle. So here there's no model. There's just like this is like a measurement. So yeah, and so okay, so then what do you do? Well, okay, so this is for instance like one of the things that we do in my lab. So we do like other kind of qubits, and we try to show that these things can have much better fidelities, and then if we place it back in the architectures of quantum computers, hopefully this will scale better with a lot less degrees of freedom. So this is what we are working on. So this is not what industry people are doing, because they claim or they want to sell a computer like as soon as possible, so they scale up. So this is another example which was in one of the exercises of chapter 1. This is like a logical qubit, which is called 0pi. So you can try to play with multiple degrees of freedom, multiple nodes, try to find a robust encoding in your electrical degrees of freedom. There's also the cat qubits. So okay, so this is from previously, so I should have removed that. But so this is, for instance, something which is done at ENS Paris. It's also done the company Alice and Bob. They use an encoding in an harmonic oscillator where they engineer 2 photon dissipation, 2 photon losses, and this gives them a bit flip time which is extremely long. So they can get 10 seconds of bit flip times, and they get a phase flip, which is not great. They get like 10 microseconds of phase flip. But the claim is that they're going to try to get rid of one error at first, and then they will just build quantum error correction in 1D, not 2D like surface code, which is expected to be a lot less overhead. So we'll see what happens. So that's the conclusion. So scaling up is very hard, but not impossible, but very hard. You need a lot of engineering, so that's good for you because you have a lot of jobs. So don't worry, you will get a job. So right now it's really the beginning of quantum error correction. Even big companies with hundreds of people and infinite money, they just don't have a logical qubit. It looks like we need better fidelities at the qubit level already to really do something useful in a realistic manner. But you can still work in the field and you don't have to do quantum computing. So it means you can also do all these other things that I showed you in the introduction. And it's also very interesting on the physics side, and it's also a very good way to have all the knowledge and experience to even pursue a career later on in industry if you want to. So with that, thank you for your attention.